So, here's something that might catch you off guard, if you're still awake enough to be caught by anything. Right now, in the dark, somewhere near your bed, there is very likely a small glowing rectangle. It might be your phone, face down on the nightstand, or a digital clock casting faint red numbers onto the ceiling, or a wireless speaker waiting quietly for a command. And inside that small object, something is happening billions of times every single second. A tiny switch is flipping on, then off, then on again. Millions of switches, perhaps billions, flipping in perfect rhythm, in a pattern someone designed, long before tonight, so that this exact moment, you lying here in the dark, listening to a calm voice, could happen exactly the way it's happening, right now, in this room. That rhythm has a name. It's called a program, and that's what we're going to spend the night with. Not in a way that demands anything from you, not in a way that requires you to memorize, or take notes, or even stay awake all the way through. Just in a way that lets the idea unfold, slowly, like someone telling you a long, meandering story about something that's always been right there, hidden in plain sight, waiting for a quiet moment like this to be understood properly. Tonight we're going to go through all of coding and programming, from the very beginning, the history, the core ideas, all the way through to how it works today, in the phone by your bed, and in the traffic lights outside your window, and in the voice reading you this sentence. We're going to explain it the way you'd explain it to a very patient 5-year-old. Slowly, with pictures made of words. No rushing, no jargon left unexplained. Every term, every concept unfolded gently, so that by the time we reach the end, you'll understand, genuinely understand, what a computer program actually is, how someone builds one, and why this strange invention, this quiet idea, has rearranged almost everything in the world around you, without most people ever stopping to notice it happening. If you fall asleep somewhere along the way, that's perfectly fine. That's the point, in fact. You don't need to catch every word. You don't need to remember what came before. The ideas will still be here, waiting, if you want to come back to them on some other night, or if your mind picks them up again halfway through, like finding your place in a familiar book. There's no test tonight, no one's checking, there's just a voice and a room, and something worth understanding, unfolding slowly enough that your mind can let go of it whenever it's ready to. So let's go back, further back than you'd expect. Before computers, before electricity, before anyone had a word for programming at all. Let's start with a very old problem. A problem that, once you see it, you'll recognize everywhere. In every machine, in every system, in every piece of technology you've ever touched. The problem is this: how do you get something that has no mind of its own to follow your instructions exactly, every single time, without ever getting bored, or confused, or creative about it? How do you take a plan that exists in your head, a sequence of steps you want carried out, and give it to something that can't think at all, and have it carry out that plan perfectly, reliably, again and again, never improvising, never wandering off, never misunderstanding what you meant? Picture a loom. Not a computer, a loom, the wooden machine people used, for centuries, to weave cloth. In the early 1800s, in France, a man named Joseph Marie Jacquard was wrestling with a very specific, very human problem. Weaving patterned fabric, the kind with flowers or shapes woven directly into the cloth, not printed on afterward, was slow, painfully slow, exhausting. A skilled weaver, someone who'd trained for years, had to lift certain threads and lower others, over and over, thousands of times, in exactly the right order, to make one single pattern appear in the fabric. It took enormous concentration, hours of focus. One mistake, one moment of distraction, one thread lifted when it should have stayed down, and the whole pattern was ruined, all that work gone. Jacquard's idea, when you hear it, sounds almost too simple, but that's often the mark of a real insight. It sounds obvious only after someone has had the courage to see it for the first time. What if the pattern itself could be written down, not in words, not in a description like, Lift this thread, now lower that one. But physically, as a series of holes, punched into a card. Where there was a hole in the card, a hook on the loom could pass through and lift a thread. Where there was no hole, the hook was blocked, and the thread stayed down. One card, one row of the pattern. String enough of these punched cards together in a sequence, feed them through the loom one after another, and the machine would weave the exact pattern the holes described. Automatically, the same way every single time, no matter who was operating it, no matter how tired they were, no matter whether they understood the pattern or not. Sit with that for a moment, because it's the seed of everything we're going to talk about tonight. A pattern, an instruction, a set of decisions, taken out of a person's head and turned into something physical, something a machine could read, something that could be repeated exactly, as many times as you wanted, with perfect consistency, something that could be saved, stored on a shelf, copied, handed to someone else in a different town, a different country, and the pattern would come out exactly the same every time. That's not weaving anymore. Not really. That's the very first appearance of an idea we now call a program. Instructions stored outside a human mind, that a machine follows in order. Let me say that again, because it's the foundation, and foundations deserve to be looked at more than once, from more than one angle. A program is a set of instructions, a plan, a sequence of steps, written down, stored somewhere outside of anyone's head so that it can be followed by something that doesn't need to understand the plan at all. It just needs to follow each step, one after another, exactly as written. The loom didn't know what a flower looked like. It didn't understand fabric or fashion or why anyone would want roses woven into their clothes. It simply obeyed the holes. Hole here, thread up, no hole there, thread stays down. Next card, next row, over and over. And out of that simple, mindless obedience, something beautiful and complex emerged. A patterned fabric, an idea made physical. Now, Jacquard wasn't thinking about computers. There were no computers to think about, but this idea, instructions stored on cards, quietly traveled forward through history, waiting for someone to notice it could be used for something other than cloth. Someone who could see that the pattern didn't have to represent flowers and leaves. It could represent mathematics. It could represent logic. It could represent any sequence of decisions and actions that could be broken down into small enough pieces. That someone, or rather, those two someones, were an English mathematician named Charles Babbage and a woman named Ada Lovelace. Ada was the daughter of the poet Lord Byron, though she never knew her father, since he left when she was an infant, and her mother, worried that her daughter might inherit what she saw as her father's unstable, overly emotional temperament, pushed her hard into mathematics and logic, thinking a rigorous, disciplined mind would keep her grounded. It's a strange, almost accidental reason for one of history's most important minds to end up exactly where she needed to be. Ada's mother, in trying to suppress poetry, accidentally cultivated a mind that could see poetry in mathematics, in a way almost no one else at the time could. In the 1830s, Babbage designed, entirely on paper, a machine he called the Analytical engine. It was never fully built in his lifetime. The precision engineering it required simply didn't exist yet. The metalworking, the tolerances, the sheer number of moving parts that would have had to work together perfectly, it was all beyond what any workshop could produce. But the design itself was staggering, even just as an idea committed to paper. It had a section for storing numbers, which he called the store. Think of it as a memory, a place where numbers could be held and retrieved. It had a section for doing calculations, which he called the mill. Think of it as the engine's hands, the part that actually performed the arithmetic. And critically, the most forward-looking part of the whole design, it was meant to be controlled using punched cards, the same idea Jacquard had used for weaving. Except now the holes wouldn't describe which threads to lift. They would describe which mathematical operations to perform, and in what order. Ada Lovelace understood something about this machine that even Babbage himself hadn't fully grasped. Babbage saw it mostly as a very sophisticated calculator, a machine that could crunch numbers faster and more accurately than a person, which was already a genuinely important goal. But Ada saw further. She wrote in her notes on the analytical engine that the machine could operate on anything that could be represented by symbols, not just numbers. She imagined it composing music, if music could be reduced to symbols and rules, harmonies and rhythms expressed as relationships that the machine could process. She wrote out, in careful, methodical detail, a sequence of operations for the machine to calculate a particular sequence of numbers, called Bernoulli numbers, a mathematical object of some subtlety. And many historians, looking back at her notes, consider this the first computer program ever written, decades before any machine existed that could run it. This is worth pausing on, because it's the real beginning of the idea we're exploring tonight. A program isn't the machine. A program is the plan. It's a sequence of exact, unambiguous steps, written down in advance, that describes what should happen and in what order. Ada Lovelace wrote a plan for a machine that wouldn't be built for another century, and might never have been built at all in the form she imagined. That's how separable the idea of a program is from any particular piece of hardware. The instructions can exist, complete and correct, even before anything exists to run them on. The plan and the machine that carries out the plan are two different things, and understanding that separation is, in a way, the beginning of understanding everything that followed. Let me put that another way, because it's subtle enough to deserve a second pass. When you think of a program, it's easy to picture the thing on your screen, an app, a website, a piece of software. But the program itself isn't the glowing pixels. It's not the device. It's the set of instructions that tells the device what to show you, what to do when you tap here or swipe there. The program is a recipe, a score, a set of directions. And just like a recipe can be written down in a book even when no one is cooking, a program can be written down and understood, in principle, even when no computer is running it. Ada Lovelace did exactly that. She wrote the recipe long before there was an oven to bake it in. For a long time after that, the idea mostly slept. Mechanical calculating machines existed, and punched cards found real, practical use. In 1890, a man named Herman Hollerith used a punch card system to help tabulate the United States Census, cutting a process that had taken years down to months. His cards held data, facts about people, their ages, where they lived, what they did for work, and his machines could sort those cards, count them, organize them in different ways, far faster than any human clerk could manage. Hollerith's company would eventually merge with others and become part of a business machines company you may have heard of, even today, called IBM. Punch cards, storing data as patterns of holes, would go on to be used for almost a century, well into the era of early electronic computers. If you've ever seen an old photograph of a computer room with stacks and stacks of paper cards, those are the direct descendants of Jacquard's loom cards and Hollerith's census cards, carrying the same simple idea forward across 150 years. But there's a difference between storing data, storing facts and numbers, and storing instructions, storing a sequence of actions. And the full realization of that difference, the idea that instructions themselves could be treated as a kind of data, something the machine reads and follows step by step, without anyone having to rewire or reconfigure anything, that full realization is what we need to look at next. Because it's the exact moment computing, as we now understand it, becomes possible. And that moment, and the problem it solved, is where we'll go when you're ready, whether that's in a few seconds or on some other night entirely. But for now, let this first section settle. The loom, the cards, the woman who wrote a program for a machine that didn't exist, the quiet idea that instructions could be stored outside a human mind, in a form something mechanical could follow. That idea, once planted, never really went away. It just waited, patiently, for the rest of the world to catch up, and that patient waiting, that slow unfolding, is what the whole rest of the story is about. Let's slow down here and really sit with the problem that needed solving, because understanding the problem is what makes the solution make sense. Often, when we look back at history, at the moments when something genuinely new came into the world, we skip past the problem too quickly. We rush toward the invention, the breakthrough, the name and the date, without ever really feeling, in our bones, what it was like to be stuck before the solution existed. So let's not rush. Let's sit with the stuckness for a while. Let's feel the weight of the problem, because the weight of the problem is exactly what makes the solution, when it arrives, feel so natural, so inevitable, almost as if it couldn't have been any other way. Imagine you have a machine, an early electronic calculating machine built in the 1940s. It's a large, humming, warm thing, filling a room with cabinets and cables and glowing vacuum tubes. And it can do mathematics, it can add, it can subtract, it can multiply, it can perform sequences of these operations far faster than any human being with a pencil and paper could ever hope to match. This is already genuinely useful. The world has problems that need calculating, artillery trajectories for the war that was raging when the first of these machines were built, complex equations for physics and engineering, census data, weather prediction, and having a machine that could crunch through the arithmetic in hours instead of weeks was a real, practical advance. But here's the catch, and it's a large catch, a catch so large that, from our perspective now, it's almost hard to believe people tolerated it for as long as they did, though of course they tolerated it because no one had yet seen the alternative. To make this machine, this fast, powerful calculating engine, do a different calculation, a different sequence of operations, someone had to physically rewire it. Not metaphorically, not by typing something new, not by feeding it a different stack of cards. Literally. Human technicians, sometimes teams of them, would spend hours, sometimes days, plugging and unplugging thick cables, flipping rows of mechanical switches, reconnecting circuits by hand, to set up the machine for a new task. Reprogramming it, though that word barely applied yet, meant physically rearranging its internal wiring. One of the very first electronic computers, a machine called ENIAC, built in the United States during the Second World War, worked exactly this way. ENIAC was designed to calculate artillery firing tables, the complex charts that told soldiers how to aim their guns given the distance, the wind, the type of shell, all the variables that affect where a projectile lands. Doing these calculations by hand, which is how they'd been done before, was slow, painstaking work, done mostly by women mathematicians, human computers as they were called then, sitting at desks for long hours. ENIAC could do the same calculations much faster once it was set up. But the setup was the problem. Changing ENIAC from one type of calculation to another meant physically replugging cables, setting switches, essentially rebuilding the machine's internal logic pathways by hand. It could take days of physical labor, just to ask the machine a new question. Picture how limiting that is. You have this enormously fast machine, this room-sized brain of wires and tubes, capable of racing through calculations at a speed that would leave any human mathematician far behind. But every time you want to ask it something different, you have to stop everything, bring in technicians, and manually, physically, rebuild its internal connections. The machine itself was blazingly fast once it was set up, but the setup, the actual instructing of the machine, the part where you told it what to do, was slow, manual, physical, and utterly separate from the machine's own operation. It was as if you had a car that could drive at 200 miles per hour, but every time you wanted to go to a different destination, you had to take the engine apart and put it back together in a new configuration before you could even start the journey. This wasn't just inconvenient. It was a fundamental limitation on what these machines could become. A machine that needs to be physically rebuilt for each new task can only ever be a specialized tool. You build it once to do one thing, you run that thing, and then you tear it down and build it again to do something else. You can't experiment quickly. You can't try something, see if it works, adjust, and try again. Not without enormous cost in time and labor. You certainly can't have a machine that switches between many different tasks fluidly, the way your phone today can be a map, a camera, a calculator, a library, and a messaging device, all within the same minute. That kind of fluid, responsive versatility was simply impossible under the old model, because the model itself said, the instructions live in the wires. Change the instructions, change the wires. The question that needed answering was this: what if the instructions themselves, the sequence of steps you wanted the machine to follow, could be stored inside the machine, the same way numbers were stored, and the machine could simply read through them, one after another, the way you might read a recipe from a piece of paper. No rewiring, no physical rearrangement, no teams of technicians spending days with cables and switches. Just feed the machine a sequence of steps, in the same form it already understood, numbers stored in its memory, and let it work through them on its own, reading each instruction, carrying it out, moving to the next, until the job was done. This idea, now called the stored program concept, is credited largely to the mathematician John von Neumann, though like most ideas of this magnitude, it built on thinking from many people working in the same period, including Alan Turing, whom we'll return to later. Von Neumann, in 1945, wrote a document describing a computer architecture where the program, the sequence of instructions, would be stored in the machine's memory right alongside the data, the numbers, that the program was meant to process. The insight, once you hear it, has the same quality as Jacquard's punched cards. It sounds simple, almost obvious, but only after someone has thought of it. The insight was this: a computer's memory doesn't need to distinguish, on a fundamental level, between numbers that represent data, a person's age, the price of bread, the current temperature, and numbers that represent instructions. Add these two numbers, move this value to a different location, compare these two quantities, repeat the previous step. Both data and instructions can simply be stored, side by side, in the same memory, represented in the same way, as patterns of bits, zeros and ones, electrical states that the machine can read and act upon. The machine reads through its memory in sequence, and when it encounters something in the part of memory that has been reserved for instructions, it treats that number not as a quantity, but as a command. Add, subtract, compare, jump to a different instruction, repeat. The same pattern of bits might mean the number 42 in one context and mean the command to add two numbers in another context. The machine doesn't care. It just follows the sequence, context switching, instruction after instruction, doing exactly what each pattern tells it to do. This is a subtle point, so let's use an analogy, gently, the way you'd explain it to a 5-year-old or to someone who's very tired and wants to understand without straining. Imagine you have a very obedient, very literal-minded assistant. This assistant cannot think for itself at all. It cannot guess what you mean. It cannot notice if something seems wrong, or inefficient, or strange. It cannot get bored. It cannot decide to do something different because it feels like it. But it can read, and it can follow instructions exactly, one at a time, in the order they're written, forever, without ever getting tired, without ever complaining, without ever needing a break. Now imagine you write this assistant a list, not a story, not a suggestion, not an idea expressed in a vague, poetic way. A list. Step 1. Pick up the red block. Step 2. Put it on top of the blue block. Step 3. If there's another red block left on the table, go back to step 1 and do it again. Step 4. Otherwise, if there are no more red blocks, stop. Your assistant reads step 1 and does exactly that. It does not wonder why you want the red block picked up. It does not consider whether the blue block might look better underneath. It picks up the red block because step 1 says to. Then it reads step 2 and does exactly that. It places the red block on top of the blue block. It does not pause to admire the stack. It does not rearrange the blocks to make them more symmetrical. It follows the instruction and moves on. Then it reads step 3, checks the condition, looks at the table, and asks itself, in its simple, mechanical way, is there another red block? If the answer is yes, It goes back to step 1 and does the whole sequence again, picking up the next red block, placing it on the stack, checking again. If the answer is no, it moves to step 4, stops, and waits, having completed the entire task exactly as specified. This is, in its simplest possible form, a computer program, a finite list of unambiguous instructions written in advance that a literal-minded follower can carry out without needing to understand why the task matters, or what the bigger picture is, or what the blocks represent. The follower doesn't need understanding, it needs clarity, exactness. A sequence it can execute, step by step, without ever having to make a judgment call. That's the problem being solved by the stored program concept. How do you write this list, this exact sequence of steps, in a form the machine can store, read, and act on entirely by itself? And how do you make that list changeable, swappable, rewritable, without having to rebuild the machine every time you want it to do something different? The stored program concept answered that question by saying, store the list in the same memory you use for everything else. Make the instructions into numbers. Let the machine read the numbers, some of which it treats as commands, some of which it treats as quantities, all flowing through the same channels, all processed by the same circuits. Now, to change what the machine does, you don't need a screwdriver or a soldering iron. You just need a new list of numbers, a new sequence, a new program. Let me say that again, slightly differently, because it's one of those ideas that rewards sitting with it for a while. Before the stored program concept, a computer's instructions were physical. They lived in the arrangement of its wires and switches. Changing the instructions meant changing the physical machine. After the stored program concept, instructions became information. They lived in memory, the same way data lived in memory. Changing the instructions meant writing new information into memory, which could be done in seconds, in milliseconds, without touching a single wire. The machine became soft, flexible, reconfigurable, not a fixed tool for a fixed purpose, but a general-purpose device that could become, at different moments, a calculator, a word processor, a music player, a map, a messenger, depending entirely on what list of instructions you fed it. This shift from physical instructions to informational instructions is one of the quiet hinges of modern history. It's the moment the computer stopped being a calculator and started being, in principle, something that could do almost anything, as long as that thing could be described in a sequence of exact, unambiguous steps. The machine itself became a blank slate, a patient, tireless, utterly literal-minded follower of whatever list you chose to give it, and the entire subsequent history of computing, the entire world we're living in tonight, with its glowing rectangles and its traffic lights, and its voice in the dark, flows directly from that shift. Now, once that idea took hold, a new question immediately appeared underneath it. It's one thing to say, we'll store the instructions as numbers in memory. It's another thing entirely to ask, how does a human being, who thinks in words and ideas and intentions, not in raw sequences of binary digits, actually write those instructions in the first place? If the program is a list of numbers, and the numbers correspond to specific commands the hardware understands, how does a person, a flesh and blood person with a mind full of concepts and goals, translate what they want the machine to do into the exact numerical sequence the machine needs? That question is what drove the entire development of programming languages, the bridge between human thought and machine instruction, and it starts with a woman we haven't mentioned yet, and a breakthrough that came from a very unexpected direction, but that's for the next part of the story. For now, let's stay with the stored program concept a moment longer. Let it settle, because it's one of those ideas that seems technical on the surface, but underneath, it's about something very simple and very deep. It's about the separation of a plan from the thing that carries out the plan. It's about the realization that instructions can be treated as a kind of data, something you can store, copy, edit, send across a wire, load from a disk, delete and replace, all without ever altering the physical machine that runs them. The machine stays the same. The machine is constant, reliable, unchanging in its fundamental operation. What changes is the program, the sequence of steps, the list of instructions, and that changeability, that softness, that ability to become something different at different moments is what makes a computer, rather than just a very fast calculator. Think about it this way. Your phone, right now, is a single physical object. It has a processor, memory, a screen, a battery. Those physical components don't change from moment to moment. The processor is the same processor whether you're reading a message or looking at a map or listening to a voice in the dark. What changes, what makes the phone a messaging device in one moment and a map in the next, is the program it's running, the sequence of instructions loaded into its memory, being read and executed, one step at a time, by that patient, tireless, literal-minded processor. The stored program concept is what makes that possible. Without it, your phone would need to be a different physical machine for every different thing you wanted it to do. With it, a single machine can be 1,000 different tools, 1,000 different assistants, depending entirely on what list you give it. This idea, that instructions can live in memory, right alongside data, that the plan and the materials can coexist in the same space, is what separates the computer age from everything that came before. And it's worth letting your mind rest on it for a moment. The image of a machine reading through a list, step by step, never knowing what it's doing, never understanding the purpose, but carrying it out anyway, faithfully, tirelessly, at billions of steps per second, while you lie here in the dark, listening to a voice that is itself the product of exactly this process, instructions stored in memory, read and executed, step after step after step, until meaning emerges from the sequence. Let's talk about the first real breakthrough, the moment programming stopped being something only a handful of specialists in raw numbers could do, and became something closer to writing, something closer to language, something a person could sit down with, learn over time, and use to express ideas, not just to wire circuits. In the earliest electronic computers with stored programs, the ones we talked about before, the machines that could hold instructions in memory instead of needing to be physically rewired, those instructions were still written in a form that was very far from anything a human mind could comfortably hold. They were written in what's called machine code. Machine code is exactly what it sounds like. It's the code the machine understands directly. Sequences of numbers, almost always expressed in binary, meaning just 2 digits, 0 and 1, that correspond directly to specific operations the machine's hardware can perform. A particular pattern of zeros and ones might tell the processor to add 2 numbers. A different pattern might tell it to move a value from one place to another. Another might tell it to compare 2 values and decide what to do next based on the result. Writing in machine code meant thinking in the machine's own language, the machine's own very limited, very precise, very literal vocabulary of operations. It was exact. It gave the programmer complete control over what the hardware did, down to the finest detail. But it was brutally tedious. Imagine trying to write a letter to a friend, except you're not allowed to use words. You can only use numbers. And every idea you want to express has to be broken down into a long sequence of simple arithmetic operations, each one represented by a specific number, typed out carefully, in exactly the right order. And if you get one single digit wrong, 1 0 where there should have been a 1, the entire letter becomes nonsense. Not just a little bit wrong, completely wrong. The machine either does something you didn't intend at all, or it simply stops, confused, unable to continue. This was programming in the very early days. It required an almost unnatural level of concentration. It required holding long sequences of numbers in your head. It required knowing, in detail, exactly how the hardware worked, exactly which number meant add, and which meant move, and which meant compare. A single misplaced digit could mean the difference between a program that worked and one that quietly did the wrong thing, or nothing at all. And the worst part was, programmers found themselves writing the same short sequences of machine instructions over and over again to accomplish the same common tasks. adding two numbers together and storing the result. Moving a piece of data from one location in memory to another, comparing two values to see which is larger. These were the building blocks of almost every program, and yet every single time a programmer needed to do one of them, they had to write out the full, exact numerical sequence, by hand, without making a single mistake. A mathematician and United States Navy officer named Grace Hopper, working in the late 1940s and early 1950s, found this frustrating in a very particular way. She wasn't just frustrated by the difficulty of it, she was frustrated by the repetition, the waste, the sheer inefficiency of having intelligent, capable people spend their time and their mental energy typing out the same sequences of numbers again and again, when those sequences could, in principle, be written once and reused. She noticed that programmers were constantly reinventing the wheel, writing the same handful of patterns over and over, wasting time and introducing errors every single time they did it. And she had an idea, a simple idea, an idea that, once you hear it, seems so natural you wonder why it took anyone so long to think of it. What if you could write a program, just once, whose entire job was to translate short, readable words closer to everyday English, into the correct sequence of machine code automatically? Instead of a programmer typing out a long string of numbers every time they wanted to add two values, what if they could simply write the word add and let a separate translating program handle the tedious, error-prone work of turning that single word into the exact numerical sequence the machine needed? The programmer would write in something closer to their own language, and the translator would convert that into the machine's language, faithfully, precisely, every single time. This translating program is what we now call a compiler, and Grace Hopper built one of the very first working examples in 1952. It's difficult to overstate how significant this idea was. It changed the entire nature of what programming meant. Before compilers, programming was the act of speaking the machine's language directly. You had to think like the machine, in the machine's terms, at the machine's level of detail. After compilers, programming became something new. You could write in a language closer to your own, a language designed for human understanding, and the compiler, a separate program running on the same machine, would handle the translation. Programming moved one level up, away from the raw hardware, towards something a human mind could hold on to more comfortably, more naturally, more like the way we think about problems in the first place. Let's slow down and really absorb this core idea, because it is the foundational concept of the entire subject, the idea that makes all modern software possible, and it deserves to be explained more than once, in more than one way, so it can settle in deeply, the way a repeated melody settles into memory. Think of it like translation between two people who speak entirely different languages. You, the programmer, are a person who thinks in words, in ideas, in intentions. You want to say something like, take this number and double it, or check whether this value is larger than that one, or repeat this sequence 10 times. The computer, at its core, doesn't understand any of those words. It only understands electrical patterns representing zeros and ones, the raw machine code we talked about. Somewhere in between you and the computer, there needs to be a translator, a faithful, precise, tireless translator who takes your readable instruction, written in a language designed for humans, and converts it into the exact pattern of switches the machine needs to flip. That translator is the compiler, or in some systems, something called an interpreter, which we'll come to a little later, which translates your instructions one at a time as the program runs, rather than all at once beforehand. But the core idea is the same, a bridge between human language and machine language. Here's the same idea again, a second way, because repetition is how understanding deepens. Imagine you're teaching someone to bake bread by mail, except the person receiving your letter cannot read English at all. They can only read a strange code made entirely of light switches, on and off, long sequences of flashes. You could, in theory, learn to write directly in that flashing code. You could memorize which sequences of flashes mean, mix the flour and water, and which sequences mean, let the dough rise. It would work. The person on the other end could follow your flashing instructions and bake the bread. But it would take you forever to learn the code, and you'd make constant mistakes, and every time you wanted to write a new recipe, you'd have to go through the same painful process all over again. Instead, you write your recipe in plain, comfortable language. Mix, knead, wait, bake, and you hire a translator, someone who has memorized exactly how to convert each of your words into the correct sequence of flashing switches. You write once, in language you understand. The translator handles the conversion every single time, perfectly. You never have to think about the switches, you just think about the bread. And a third way, because a sleepy mind often benefits from hearing the same truth from multiple angles. A programming language is a bridge. On one side of the bridge stands a human being, thinking in ideas, patterns, goals, intentions. On the other side stands the machine, understanding only precise, mechanical, binary instructions, patterns of electricity, on and off. The compiler, or interpreter, is the bridge itself. It carries meaning safely from one side to the other, so the human never has to wade into the raw river of ones and zeros directly. The human stays on the human side. They write in a language that feels, if not exactly natural, at least learnable, readable, expressive. The compiler handles the crossing, faithfully, every time. Grace Hopper's compiler work eventually led to a language called COBOL, designed for business use, one of the very first widely adopted higher-level programming languages. The term higher level here simply means a language written closer to human words and concepts than to raw machine instruction. It's higher in the sense that it sits further from the hardware, closer to the human. COBOL let business programmers write things that looked, at least a little, like English sentences, describing calculations and data processing tasks in a way that was far more readable than the numerical machine code it replaced. Around the same period, a language called Fortran was developed for scientific and mathematical calculation, led primarily by a team at IBM under a mathematician named John Backus. Fortran, whose name came from formula translation, let scientists and engineers write something resembling the algebraic formulas they already knew from their training. Instead of translating their equations by hand into machine code, a painstaking and error-prone process that could take days or weeks for a complex calculation, they could write something close to the math itself, and the Fortran compiler would handle turning that into machine code automatically. This saved enormous amounts of time. More than that, it opened up programming to people who were experts in science and engineering, not just experts in the internal workings of a particular computer. This is the moment programming stopped being purely an act of instructing hardware and became something closer to an act of expressing an idea. An idea written in a language designed for human clarity, with a faithful, invisible translator doing the difficult work underneath. The programmer could think about the problem they were trying to solve, the physics of an artillery shell, the payroll calculations for a company, the statistical analysis of an experiment, rather than thinking about which specific memory location held which specific number, or which exact binary code meant add versus add with carry. The compiler handled those details, the programmer handled the ideas. Now, this separation between the idea and the implementation, between what you want to do and exactly how the machine does it, is one of the deepest patterns in all of programming. It's a pattern we'll see again and again, in different forms, at different levels. Each time, the story is the same. Something that was once done manually, painstakingly, by a person holding all the details in their head, gets handed off to a program, a translator, an automated process, so the person can think at a higher level, closer to the problem, further from the machinery. Compilers were the first great example of this pattern, but they were far from the last. Now let's look at how that first breakthrough was built upon, layer after layer, because the story doesn't stop with compilers. It grows, steadily, into something much richer. Once higher-level languages existed, once programmers could write things like add and move and compare, instead of long strings of binary digits, the next natural question was, What should these languages be able to express? Early languages were mostly about doing calculations in sequence. Step 1, then step 2, then step 3. A straight line from beginning to end, with perhaps a few branches along the way. But real problems, the kinds of problems people actually need to solve with computers, are rarely that simple. Real problems involve making decisions. Real problems involve repeating things many times, but not always the same number of times. Real problems involve organizing large amounts of work into manageable, reusable pieces, so you don't have to write the same logic over and over throughout a long program. Real problems are messy, branching, looping, layered, and the early higher-level languages, as useful as they were, didn't yet have clean, simple ways to express all of that messiness. These needs led to a set of ideas that, together, form the backbone of nearly every programming language that came after. These ideas are so fundamental that, once you understand them, you'll see them everywhere, in every piece of software, in every app, in every system, in the voice reading you this sentence right now. They are the basic vocabulary of programming, the nouns and verbs and sentences out of which all software is built. And we're going to sit with them slowly, one at a time, because this is genuinely the heart of what programming is, not the hardware, not the history, not even the languages themselves. These 4 ideas, these 4 simple, almost childishly simple concepts. Once you have them, you have the foundation of everything. The first idea is the variable. Think of a variable as a small, labeled box. It's a box you can put something into, a number, for instance, or a word, or almost anything else, depending on the language you're using. The box has a label, a name you give it, like age or score or temperature or player name. You can put something inside the box, and you can look inside the box later to see what's there, and you can change what's inside the box whenever you want. That's the key. The contents can vary, hence the name, variable. If you have a box labeled age, you might put the number 7 inside it. Later in your program, you might take out the 7, add 1 to it, and put 8 back in. The label age always stays the same. It's always the same box. But what's inside the box can change. It can be 7 at one moment and 8 at another. This is what a variable is, a labeled place to store something that might be different at different points in time. A container for information that your program can refer to, update, and use as it works through its instructions. Think about the phone by your bed. It has variables inside it right now in the programs it's running. A variable holding the current battery percentage, a variable holding whether the screen is on or off, a variable holding the last time you touched the screen. Each of these is a labeled box, a named container, that the program can check and update as needed. The second idea is the conditional, often written in programming languages as an if statement. This is how a program makes a decision. If a certain thing is true, do this. Otherwise, do that instead. Picture again our very obedient, literal-minded assistant from earlier. You might tell it, if it's raining outside, bring an umbrella. Otherwise, if it's not raining, don't bother. Your assistant checks the condition. Is it raining? It looks outside, or checks a sensor, or reads a weather report, however it gets its information. Based on the answer, it chooses one path or the other. Bring the umbrella or leave it. This is the entire idea behind every decision a computer program ever makes, at every scale, from the simplest calculator to the most sophisticated software running today. Somewhere, deep inside, it comes down to this. If this is true, do this. Otherwise, do that. A fork in the road. A choice between 2 paths. The program checks something, and based on what it finds, it follows one set of instructions or a different set. The third idea is the loop. This is how a program repeats something without a human having to write it out again and again. Remember our assistant stacking blocks. Pick up a red block. Put it on the blue block. If there's another red block, go back and do it again. That repeating instruction, go back and do it again, until some condition is met, until there are no more red blocks, is a loop. Loops are what let a program count from 1 to 1,000,000 without a person typing out 1,000,000 separate lines. They're what let a video game check 60 times every second whether you've pressed a button. They're what let a weather model run the same calculation across millions of tiny sections of the atmosphere, one after another, automatically. A loop is a way of saying, do this, and then do it again, and again, and again, until something tells you to stop. It's repetition, automated. It's one of the things computers are best at, repeating tasks without ever getting tired or bored or sloppy. The fourth idea is the function, sometimes called a procedure or a subroutine or a method, depending on the language and the context. This is a way of giving a name to a reusable chunk of instructions, so you can use it again and again without rewriting it every time. Imagine you taught your assistant a specific useful sequence. Wash a cup, rinse it, dry it, put it away. And you gave that whole sequence a name, say, clean cup. From then on, instead of writing out all 4 steps every single time you needed a cup cleaned, you could simply say, clean cup, and your assistant would know exactly what that meant and would carry out all 4 steps in order, without you having to specify them again. Functions let programmers do the same thing with code. Build a small, well-understood, reliable piece of logic, give it a name, and then use that name whenever you need that logic, as many times as you need it, throughout your program. Functions let you build up from small pieces to larger pieces, combining and recombining, without ever having to think about all the tiny details at once. They are the primary tool for managing complexity, for taking something large and making it understandable by breaking it into named, reusable parts. Variables to hold information, conditionals to make decisions, loops to repeat things, functions to organize and reuse. These 4 ideas, on their own, sound almost too simple to explain something as vast as modern software. But nearly everything you interact with on a screen, a messaging app, a video game, a map, a browser, the very voice reading you this sentence right now, is built, at its foundation, from combinations of exactly these 4 ingredients, layered and combined, over and over, by thousands of people, across decades. The complexity doesn't come from having more ideas. It comes from combining these few ideas in an enormous number of ways, building larger structures out of smaller ones, like constructing a cathedral out of bricks. The bricks are simple, the cathedral is not, but the cathedral is still, at bottom, just bricks, arranged with care and intention. Let's rest here for a moment. If you're still with me, let your eyes close now if they aren't already. You don't need to follow every word from here. Just let it settle, the way warm water settles around you in a bath, slowly, without effort. The explanation continues either way, whether you're catching every word or drifting somewhere between listening and sleep. There's no test. There's no need to hold on tightly. The ideas will be here, and if your attention slips away for a while, that's exactly what your mind is supposed to do at this hour. Let's move now into the core mechanics, the actual workings, how all of this really operates underneath the surface. We've talked about the history, the loom, the cards, the woman who wrote a program for a machine that didn't exist. We've talked about the stored program concept, the idea that instructions could live in memory right alongside data. We've talked about compilers, the translators that let humans write in something closer to their own language. And we've talked about the 4 fundamental ideas: variables, conditionals, loops, and functions. Now let's go deeper into the machinery itself, into what actually happens, moment by moment, when a program runs. Because there's something genuinely beautiful, in a quiet, mechanical way, in seeing how a handful of simple pieces combine into something so capable. Think about how a computer actually reads a program. Deep inside every computer, every phone, every device you've ever used, is a small, incredibly fast component called a processor, or more specifically, a central processing unit. Its entire job, its only job, is to read one instruction, carry it out, and then move to the next instruction, over and over. That's it. That's the whole engine. Read an instruction, execute it, move to the next. Read an instruction, execute it, move to the next. Millions of times per second. Billions of times per second in the devices we have today. It has no imagination. It has no sense of the bigger picture. It does not know if it's calculating a weather model, or rendering a video, or running the program that generates this very voice. It simply reads the next line, does exactly what it says, and moves forward. That's it. That's the whole engine underneath everything. This repetitive cycle, read, execute, move forward, read, execute, move forward, is called the fetch-execute cycle, and it's been the heartbeat of computing since the very first stored program machines. The processor reaches into memory, fetches the next instruction, decodes what it means, performs the required operation, and then moves its internal pointer to the next instruction in the sequence. Then it does it again, and again, and again, at a speed that is genuinely hard for a human mind to grasp. The processor in your phone, the one resting near your bed right now, can do this billions of times per second. Billions. In the time it takes you to draw one breath, it has fetched and executed more instructions than there are people on Earth. And every single one of those instructions was something simple. Add these two numbers, compare these two values, move this piece of data from here to there, jump to a different point in the sequence if a certain condition is true. Nothing more complicated than that. Nothing that would impress anyone. Taken on its own. Just tiny atomic operations, performed with relentless, mindless fidelity. Now, here's where it becomes almost magical, in a quiet, mechanical way. Because the processor can do this so fast, and because a program can tell the processor to jump backward to an earlier instruction, or skip forward past some instructions, based on a condition, extraordinarily complex behavior can emerge from an extraordinarily simple process. It's a little like how a single ant, following a few very basic rules, seems mindless on its own. A single ant doesn't know how to build a colony. It doesn't have a blueprint in its head. It doesn't understand architecture or ventilation or agriculture. But an entire ant colony, made of thousands of ants each following those same simple rules, can build elaborate tunnels, farm fungus, store food, and defend against invaders. No single ant understands the colony, but the simple rules, repeated at scale, produce something that looks, from a distance, like genuine intelligence, like planning, like purpose. A computer program works the same way. No single instruction, add one, compare two numbers, jump to a different line, is remotely intelligent on its own. No single instruction knows what the program is trying to do. No single instruction understands the problem being solved. But when you string together thousands or millions of these simple instructions, using loops to repeat, conditionals to branch, and functions to organize, you can produce something that recognizes your face in a photograph, something that translates your voice into text in real time, something that calculates the safest and most fuel-efficient path for an airplane to land in a storm. The complexity emerges not from the instructions themselves, but from the sheer number of them, the speed at which they're executed, and the patterns in which they're arranged. Simple pieces, combined in clever ways, at enormous scale, produce complex behavior. That's the core principle of software. That's how a handful of basic ideas, variables, conditionals, loops, functions, can give rise to everything from a calculator to a voice in the dark. Let's walk through a small, complete example, slowly, the way you might walk through a recipe with someone learning to cook for the first time. Not because this example is complicated, it's not, but because seeing how the pieces fit together in a concrete case makes the abstract ideas feel real, feel solid, feel like something you could hold in your hand. Suppose you want a very simple program that decides whether a number is even or odd. An even number is one you can split perfectly in half, with nothing left over, like 2, or 4, or 6, or 100. An odd number always has one left over when you try to split it, like 3, or 5, or 7, or 99. This is a simple distinction, one we learn as children. But how would you teach it to our literal-minded assistant? the one who can follow instructions perfectly but cannot think for itself at all. You'd start with a variable. A variable, remember, is just a labeled box. Let's call this box number, and let's put a number inside it. Say, the number 7. 7 is our test case. We want the program to tell us, correctly, that 7 is odd. Then you'd use a mathematical operation that's a little unusual in everyday life but very useful in programming, something called finding the remainder. If you divide 7 by 2, you get 3, with 1 left over. That leftover amount, the one that doesn't fit evenly into the division, is called the remainder. The remainder is exactly what tells you whether a number is even or odd. If the remainder, after dividing by 2, is 0, then nothing was left over, and the number is even. If the remainder is 1, then something was left over, and the number is odd. That's the whole logic, dividing by 2 and looking at what's left over. So your program would say, in plain words, roughly this. Take the number in the box, divide it by 2, look at the remainder. If the remainder is 0, say the word even. Otherwise, say the word odd. That's a conditional, an if statement, doing exactly what we described earlier, checking something and choosing one of two paths based on what it finds. If the remainder is 0, follow the path that says even. Otherwise, follow the path that says odd. 2 paths, 1 decision. The entire logic of even and odd, captured in about 3 lines of instruction. Now imagine you don't just want to check one number, you want to check every number from 1 to 100, and print out, for each number, whether it's even or odd. Rather than writing this same check 100 separate times, you'd wrap it in a loop, something like this. Start with the number 1, check whether it's even or odd, print the result, then increase the number by 1, so it becomes 2. Check again, print again, increase again. Keep going, keep repeating. Stop when you've passed 100. The loop handles the repetition. The conditional handles the decision. The variable holds the current number as it changes. 1, then 2, then 3, all the way up to 100, each time through the loop. 3 of our 4 core ideas, variable, conditional, and loop, working together in about 4 or 5 lines of instruction to do something that would take a person quite a while to do by hand, checking 100 numbers one by one. And the computer does it in a fraction of a second. Not because any single step is clever, but because it can perform those simple steps, fetch, execute, move forward, so blindingly fast that 100 iterations, 100 trips through the loop, is essentially nothing. Now let's zoom out from this tiny example and talk about how programs are organized at a larger scale. Because real software isn't 4 lines long. Real software, the kind running on your phone or your laptop or the servers that power the internet, is often millions of lines long. Written by teams of people, sometimes hundreds of people, over many years, with different parts written at different times by different hands. How do you keep something that large from collapsing into chaos? How do you hold that much complexity in a way that human minds can still understand, still modify, still improve? This is where functions really earn their importance. We introduced functions earlier as a way to give a name to a reusable chunk of instructions. But at scale, they're more than just a convenience. They're the primary tool for managing complexity. Imagine a large program, something like the software running a messaging app. Inside it, there might be a function specifically responsible for sending a message, another function responsible for checking whether new messages have arrived from the server, another for showing a notification on the screen, another for saving a photo you've attached to a message, another for compressing that photo so it takes up less space, another for encrypting the message so it can't be read by anyone other than the person you're sending it to. Each of these functions is a self-contained, well-understood unit, a small, reliable piece of the overall puzzle, built and tested somewhat independently, often by different people, and then connected together through the simple mechanism of one function calling another by name. When the part of the program that handles sending a message needs to encrypt the message before it goes out, it doesn't need to know how encryption works. It doesn't need to contain all the complex mathematics of cryptography inside itself. It simply calls the encryption function by name, hands over the message text, and receives back the encrypted version. It trusts the encryption function to do its job correctly. It only needs to know what the function does, not how it does it. This separation of concerns, this hiding of complexity behind simple named interfaces, is what allows software to grow to enormous sizes without becoming completely unmanageable. This idea of building complex systems out of smaller, independently understandable pieces echoes something you'll find throughout human engineering, long before computers existed. A car isn't designed as one impossibly complicated object. No single engineer holds the entire car in their head, every bolt, every wire, every weld. Instead, the car is an engine, connected to a transmission, connected to wheels, connected to a steering system, connected to a braking system, each one a distinct, well-defined unit that specialists can design somewhat separately, and then connect together through agreed-upon interfaces. The engine team doesn't need to understand the details of the braking system. The braking system team doesn't need to understand the internals of the transmission. They just need to agree on how their pieces connect. Software works the same way. Functions calling other functions, organized into larger structures called modules or libraries or packages, so that no single person ever has to hold the entire staggering complexity of a large program in their mind all at once. They only need to understand the piece they're working on and the interfaces through which it connects to everything else. There's another core mechanic worth explaining gently here, something called data structures. We've talked about variables, single-labeled boxes that hold one piece of information, but real programs rarely deal with just one piece of information at a time. They deal with collections, lists of things, sets of things, mappings between things. And organizing these collections in ways that make sense for the problem at hand is what data structures are all about. If a variable is a single labeled box, a data structure is a way of organizing many boxes together, in a shape that fits the kind of information you're working with. Imagine a list. A list is simply many boxes lined up in a row, each one holding an item, and each one having a position, first, second, third, fourth, and so on. A program might use a list to hold every song in a playlist, or every message in a conversation, or every player's score in a game. Instead of creating a separate, individually named box for every single song, you create one list, one ordered sequence, and the program can add items to the end of it, remove items from the middle, look at the item in a particular position, or walk through the whole list, one item at a time, using a loop. Exactly the mechanic we already understand. There are other shapes information can take too. Imagine, instead of a single row of boxes, a structure where each box has a small note attached to it, like a label with a keyword, and you can look up a box directly by that keyword, instead of having to search through the whole row. If you wanted to find a particular person's phone number, you wouldn't want to look through a list of every phone number in the city, one by one, until you found the right name. You'd want to go directly to the entry labeled with that person's name and find the number there. This kind of structure, where you look things up by a key rather than by a position, is often called a dictionary or a map in programming terms. It's what lets a program quickly find the meaning of a word, or the price of a product given its code, or a person's address given their name, without having to check every single item in a long list one at a time. There are other structures too, structures shaped like trees, with branches and leaves, useful for organizing information that has a natural hierarchy, like the folders on your computer, or the chapters and sections of a book. Structures shaped like webs or graphs, useful for representing connections and relationships, like the network of roads in a city, or the links between pages on the internet. The variety of data structures is large, and computer scientists have spent decades studying which shapes work best for which kinds of problems. But the underlying idea is always the same. You take the simple labeled box, the variable, and you arrange many of them together in a pattern that makes the information easy to access, easy to update, and easy to reason about. Take a slow breath here. We've now covered the actual mechanical core of how programs work. Instructions read one at a time by a processor, fetched from memory, executed, and then the next one fetched, over and over, billions of times per second. Variables holding changeable information, single labeled boxes that can contain different values at different moments. Conditionals making decisions, checking something and choosing between two paths. Loops repeating actions, doing the same thing again and again until a condition is met. Functions organizing reusable pieces, giving names to sequences of instructions so they can be called upon whenever needed. And data structures organizing collections of information in shapes that fit the problem, lists and dictionaries and trees and graphs, all built from the same humble variable, arranged in different ways. Every piece of software you've ever used, no matter how sophisticated it seems from the outside, no matter how smooth the animation or how responsive the interface, or how intelligent the behavior, is built from combinations, layered again and again, of exactly these ingredients. The messaging app that lets you talk to someone on the other side of the world, the map that shows you how to get home, the camera that captures a moment and stores it as a pattern of colored dots, the voice reading you this sentence right now. All of it, at the bottom, is variables and conditionals and loops and functions and data structures arranged by human minds, translated by compilers or interpreters, and executed by a processor that has no idea what any of it means. The processor doesn't know it's running a messaging app. It doesn't know what a message is. It doesn't know what a friend is, or a conversation, or a notification. It simply fetches an instruction, executes it, and moves to the next. Fetches, executes, moves forward. Billions of times per second. And out of that mindless, repetitive cycle, meaning emerges. Not inside the machine. The machine has no room for meaning. Meaning emerges in you, the person using the machine, the person reading the message, hearing the voice, seeing the photograph. The machine is just the carrier, the faithful, tireless executor of whatever sequence of simple steps it's been given. The meaning happens somewhere else. It happens in the space between the machine and you. Now let's talk about the variations, the different branches this core idea grew into. Because once these fundamental building blocks existed, once programmers had variables and conditionals and loops and functions, once they had compilers to translate their readable code into machine instructions, something interesting started to happen. Different communities of programmers, working on different kinds of problems, began to arrange these same basic ingredients in different styles. Not different in the sense of being completely unrelated, they all still used variables, conditionals, loops, and functions, but different in how they organized those pieces, how they thought about the structure of a program, what they emphasized and what they chose to keep in the background. These different styles are worth understanding, slowly, one at a time, not because you need to become an expert in any of them, but because seeing the variations helps you understand the core. It's like looking at a family of related languages. Once you see how French and Spanish and Italian all grew from the same Latin roots, you understand something deeper about each of them, and about the roots themselves. The same is true here. The different styles of programming are all, at bottom, built from the same few ideas. But the way those ideas are arranged, the philosophy behind the arrangement, tells you something about what kinds of problems each style was trying to solve. The earliest style, the one closest to what we've already described, is called procedural programming. In this style, a program is essentially a list of instructions, executed largely in order from top to bottom, organized into functions that call each other as needed. It's very close to a recipe. Step 1, Step 2, Step 3, with occasional loops to repeat things and conditionals to make decisions along the way. The focus is on the sequence of actions, what should happen first, what should happen next, what should happen if this condition is true, what should repeat until that condition changes. The program is a procedure, a set of steps to be followed. Languages like the early versions of Fortran, which we talked about before, worked primarily in this style. and a very influential language called C, developed in the early 1970s by Dennis Ritchie at Bell Labs, refined the procedural approach into something powerful and enduring. C gave programmers a language that was still fairly close to how the hardware actually worked, meaning programs written in C could be fast and efficient, but it was also far more readable and manageable than raw machine code. You could write in C and have the compiler produce efficient machine instructions, without having to think about the specific binary codes for every operation. A great deal of foundational software, including much of the software that operating systems themselves are built from, traces its lineage back to C. If you're using a phone or a laptop right now, there is almost certainly code written in C, or in languages directly descended from C, running deep inside it, managing memory, handling files, talking to the hardware. Procedural programming works well for many problems. When what you need to do can be described as a clear sequence of steps, a procedure, then writing it as a procedure makes intuitive sense. Calculate this, then check that, then loop back and do it again, then call this other function to format the result. The structure of the code mirrors the structure of the task. It's straightforward, it's learnable, it's still, in many contexts, the most natural way to think about programming. But as programs grew larger and more complicated, a different set of challenges emerged. When a program has hundreds of thousands of lines of code, when it's being worked on by dozens or hundreds of people, when it needs to be maintained and updated over many years, the procedural approach can start to feel strained. The problem isn't that procedures stop working. It's that keeping everything organized, keeping the data and the functions that operate on that data from becoming tangled together in ways that are hard to understand and hard to change, becomes increasingly difficult as the system grows. Imagine a large program written in a purely procedural style. You have variables holding all kinds of information, customer names, account balances, product prices, inventory counts, and you have functions that operate on that information, functions that calculate discounts, functions that process orders, functions that update inventory, functions that generate reports. As the program grows, these functions become deeply interconnected. A function that processes an order might need to call the function that updates inventory, which might need to call the function that checks for low stock, which might need to call the function that sends a notification. The web of connections becomes dense and complicated. Changing one function might have unexpected effects on other functions that depend on it, in ways that are hard to predict and hard to test. The data, the information the program works with, becomes shared across many functions, and keeping track of which function changed which piece of data, and when, and why, becomes a major source of errors. Out of this challenge, a different style emerged. It's called object-oriented programming. The idea here is to organize a program not just as a list of steps, not just as a collection of functions that pass data around, but as a collection of things, called objects, each of which bundles together some information and the specific actions that make sense for that particular kind of thing. Instead of having data floating around separately from the functions that operate on it, you keep related data and related functions together in the same object as a single, self-contained unit. Let's use a gentle analogy. Imagine you're modeling a zoo inside a computer program. You want the program to keep track of the animals, what they eat, how they move, how they interact. In a purely procedural style, you might have separate lists of information, a list of animal names, a list of animal ages, a list of animal species, and then separate functions for feeding, separate functions for moving, separate functions for making sounds. All of this data and all of these functions would be somewhat loosely connected, and it would be your job as the programmer to make sure that when you called the feed function, you passed it the right animal's data, and that the feed function knew which species of animal it was dealing with, because a lion and an elephant eat very different things. In an object-oriented style, instead, you'd define something like a blueprint for what an animal is. This blueprint says every animal has a name, an age, a way of eating, and a way of moving. The blueprint describes the general idea of an animal, the properties every animal has, and the behaviors every animal can do. Then you'd create individual objects from that blueprint. This particular lion, named Leo, 3 years old. This particular elephant, named Ella, 12 years old. Each object carries its own information, its own name, its own age, and each object has its own version of the shared behaviors. Both Leo and Ella can eat, but the eating function for a lion does something different from the eating function for an elephant. The object knows, internally, what kind of thing it is, and what the right way to perform each behavior is for that particular kind of thing. This bundling together of information and the actions that operate on that information is the central idea of object-oriented programming. The object protects its internal information. You don't directly reach into an animal object and change its age from the outside. Instead, you ask the object to do something, like have a birthday, and the object updates its own age internally, in whatever way is correct for that kind of object. This makes large programs easier to reason about, because the interactions between different parts of the system happen through well-defined interfaces, rather than through every function having access to every piece of data. You can change how an object works internally, as long as it still responds to the same requests from the outside, and the rest of the program doesn't need to know anything changed. This style was developed significantly through languages like Smalltalk in the 1970s, and later popularized by languages like C++ and Java, which became widely used in the 1980s and 1990s. It became especially useful for large, complex software, the kind with graphical interfaces, buttons and windows and menus, where it's natural to think of each visible element as an object with its own properties, its position, its size, its color, and its own behaviors, what happens when you click it, what happens when you hover over it. Object-oriented programming let programmers organize huge systems into understandable, self-contained pieces that modeled real-world or conceptual things directly. A third style, older in some ways than either of these but influential in a different direction, is called functional programming. This style leans heavily on the idea of pure functions. A pure function is a function that, given the same input, always produces exactly the same output, with no side effects. No hidden changes to anything else in the program. No modifying of variables that exist outside the function. No reading from some global state that might have changed since the last time the function was called. The function is a clean, mathematical mapping from input to output, and nothing else. This might sound restrictive. Why would you want to limit yourself to functions that can't change anything? But the benefit is predictability. When you call a pure function, you know exactly what will happen. It will take the inputs you give it, perform some calculation, and return a result. It will not, as a hidden side effect, modify some variable that another part of the program is relying on. It will not behave differently depending on what day of the week it is, or what the user did 3 steps ago. The same inputs, always, unfailingly, the same output. This makes certain kinds of complicated software, particularly things involving many things happening at once, much easier to reason about correctly. When you have many different parts of a program running concurrently, and they're all sharing and modifying the same data, it becomes very difficult to predict what state the system will be in at any given moment. Pure functions, by refusing to modify shared state, sidestep this entire class of problems. Functional programming draws heavily from mathematics, particularly a branch of logic developed by a mathematician named Alonzo Church in the 1930s, called lambda calculus. Lambda calculus described computation itself purely in terms of functions applied to other functions, with no variables, no state, no side effects, just functions all the way down. It was a theoretical model of computation, a way of reasoning about what could and could not be computed, long before electronic computers existed. But it turned out to be a remarkably useful practical model as well. Languages like Lisp, developed in the late 1950s, and later languages like Haskell, built heavily around these ideas. And even in languages that aren't primarily functional, the habit of writing pure functions when possible, of minimizing hidden state and side effects, has become widely recognized as good practice. It's worth understanding gently that these styles aren't rigid, separate worlds. They aren't like different religions, where you have to pick one and reject the others. Many modern programming languages, things like Python, JavaScript, Swift, and many others, freely borrow ideas from all three styles. They let you write in a procedural style when the problem calls for a clear sequence of steps. They let you organize your code into objects when you're modeling things that have state and behavior, and they let you write pure functions when you want predictability and safety. A skilled programmer moves between these styles, choosing whichever approach fits the particular problem they're solving at that moment. Programming languages, much like spoken languages, evolve and borrow from one another constantly. They pick up features that worked well in other languages, adapt them, and combine them in new ways. The history of programming languages is not a history of sharp breaks and revolutions. It's a history of gradual, cumulative improvement, layer building on layer. There's another important variation worth mentioning here, and it concerns not how programs are organized, but how they're translated and run. Earlier, we talked about compilers, the programs that translate your readable code into machine instructions all at once, before your program ever runs. You write your code, you run the compiler, it produces a finished, translated version, and then you can run that translated version as many times as you want, without needing the compiler again. This is how languages like C and C++ typically work. But there's a second common approach, called interpretation. In this approach, there is no separate translation step that happens ahead of time. Instead, a separate program, called an interpreter, reads your code and translates it into action, one instruction at a time, as the program runs. The interpreter is like a simultaneous translator, listening to you speak and translating each sentence as it comes, rather than waiting for you to finish your entire speech and then translating the whole thing at once. Languages like Python and JavaScript are commonly run this way. You write your code, and then you hand it to the interpreter, which reads it line by line, figure out what each line means, and carries it out immediately. There are trade-offs between these two approaches. Compiled programs tend to run faster once they're translated, because all the translation work happened ahead of time. The finished program is already in the machine's native language, so the processor can just execute it directly, without any translation overhead. Interpreted programs, on the other hand, tend to be more flexible and quicker for a programmer to test and adjust. You can write a line of code, run it immediately, see what it does, change it, and run it again, without waiting for a separate compilation step. This makes interpreted languages popular for learning, for experimentation, and for situations where the speed of writing and testing code matters more than the raw execution speed of the finished program. And in practice, the line between compilation and interpretation has become quite blurry over the years. Many modern systems use a mix of both approaches. They might do some translation ahead of time, enough to make the code run reasonably fast, and then finish the translation on the fly while the program is running, adapting to the specific conditions of that particular execution. The world is rarely as simple as a clean either-or distinction. But the underlying concepts, translation ahead of time versus translation on the fly, remain useful ways to think about the different paths a program can take, from the text a programmer writes to the actions a processor performs. Take a slow breath here. We've covered the main styles: procedural programming, the style of recipes and sequences; object-oriented programming, the style of things that bundle together information and behavior; functional programming, the style of pure, predictable functions with no hidden side effects. And we've talked about compilation and interpretation, the two main ways that human-readable code gets turned into machine-executable instructions. None of these are the one true way. They're all tools, different lenses for thinking about the same fundamental task, which is telling a literal-minded machine what you want it to do, in a way that is clear, correct, and maintainable by other human beings. These styles, these approaches, these philosophies, all emerged from the same root, the same four ingredients: variables, conditionals, loops, functions. The variations are in how you arrange them, how you organize them, what you emphasize, and what you choose to keep hidden. But underneath, The machine is still doing exactly the same thing it has always done, fetching an instruction, executing it, moving to the next, billions of times per second. The machine doesn't know if it's running procedural code or object-oriented code or functional code. It doesn't care about the philosophy behind the arrangement. It just reads instructions, one after another, and does what they say. The styles are for us, for the humans, ways of thinking that help us manage complexity, that help us write code that works, that help us collaborate with each other across time and distance. The machine doesn't need them, we do. Let's talk about one more extension because it's central to almost everything you use today, and it's the part of the story where programming stops being about a single machine, alone in a room, and becomes about connection. About machines talking to other machines, across rooms, across cities, across oceans, until the whole planet is wrapped in a web of programs sending messages back and forth, constantly, silently while you sleep. A single program running on a single machine, doing its own calculations, reading its own instructions from its own memory, was the whole story for decades. The early computers we've talked about, ENIAC, the machines Grace Hopper worked on, the first machines to run Fortran and COBOL, they were islands. They sat in their own rooms, in their own buildings, and they computed whatever was fed into them, and then they stopped and waited for the next task. They didn't talk to other computers because there were no other computers to talk to, or at least very few, and no easy way to connect them even if you wanted to. The idea of a network, of multiple computers exchanging information in something like real time, was still mostly theoretical, something researchers were beginning to think about, but hadn't yet built. But starting in the 1960s, and accelerating enormously through the 1970s and 1980s, that began to change. Computers started connecting to each other. First, through research networks, small experimental systems built by universities and government agencies to see if it could be done at all. One of the most important of these early networks was called ARPANET, developed by an agency within the United States Department of Defense called ARPA, the Advanced Research Projects Agency. ARPANET began as a way to connect computers at a handful of research institutions so that researchers could share computing resources and collaborate more easily. It was a small network, just a few nodes at first, but it was the seed from which something much larger would grow. This connection, this linking of separate machines into a single communicating system, required a new layer of ideas, on top of everything we've already discussed. It wasn't enough to have programs that could run on a single machine. You needed programs that could send information to a different machine, potentially a machine built by a different company, running a different operating system, located in a different city or a different country, connected by wires that might be noisy or slow or prone to cutting out at unexpected moments. You needed the information to arrive intact, in the right order, without anything lost or scrambled along the way. And you needed all of this to happen reliably, automatically, without a human operator having to manage every step of the process. To make this possible, the computing community, over many years and through the work of many people, developed something called protocols. A protocol, in this context, is an agreed-upon set of rules for how to communicate. It's not a program itself, it's a description, a standard, that any programmer can implement in their own software, so that different programs, running on different machines, can understand each other. Think of it like the rules of diplomatic correspondence. There are certain forms that letters between governments are expected to follow, certain ways of addressing each other, certain formats for requests and responses. If both sides follow the same rules, communication is possible even if they speak different languages internally. Protocols serve the same function for computers. One of the most foundational sets of protocols, developed in the 1970s by researchers including Vint Cerf and Robert Kahn, is a pair called TCP and IP. IP stands for Internet Protocol. Its job is to handle the addressing. Every machine on a network that uses IP gets a unique number, an IP address, that identifies it. When you send information to another machine, the IP protocol handles the task of getting that information from your machine to the correct destination, routing it through whatever intermediate machines are necessary along the way. It's the digital equivalent of writing an address on an envelope. TCP stands for Transmission Control Protocol. Its job is to handle the reliability. When you send a message using TCP, the protocol breaks your message into small pieces called packets, sends them across the network, and then reassembles them correctly on the other end. If some packets arrive out of order, TCP puts them back in the right order. If some packets get lost entirely, TCP notices they're missing and asks for them to be sent again. To the program using TCP, it looks like a reliable, continuous connection, a pipe through which data can flow. Underneath, the reality is messier, packets taking different routes, arriving at different times, sometimes disappearing and needing to be resent. But TCP hides all of that complexity. It provides an abstraction, a simplified view of the network that programs can rely on without having to worry about the messy details. On top of TCP and IP, many other protocols have been built, each designed for a specific kind of communication. There are protocols for sending email, protocols for transferring files, protocols for loading web pages, protocols for streaming video, protocols for making voice calls. Each of these is a set of rules, agreed upon by the community, that lets programs written by different people, at different times, for different purposes, communicate with each other smoothly. When you open a messaging app on your phone and send a message to a friend who might be across town or on the other side of the world, an enormous, invisible sequence of programs, following these protocols, springs into action. Your message, that string of words you typed, is handed off to a series of software layers. One layer breaks it into packets, another layer addresses each packet with the destination's IP address. Another layer sends the packets out over whatever network connection your phone is using, Wi-Fi or cellular data. The packets travel through a chain of routers, specialized machines whose entire job is to read the address on each packet and forward it in the right direction, closer to its destination. These routers might be in your home, in your internet provider's building, in larger regional hubs, on undersea cables crossing oceans, in data centers on other continents. Each router examines the address and passes the packet along, like a relay runner handing off a baton, until the packets reach the destination machine, your friend's phone or a server somewhere. On that destination machine, the TCP layer reassembles the packets into the original message, checking that nothing is missing, requesting resends if needed. Then the messaging app on your friend's phone receives the reassembled message and displays it on the screen. All of this, the breaking apart, the addressing, the routing, the reassembly, the display, happens in a fraction of a second, often fast enough that it feels instantaneous to both of you. And every step of this process is a program, or part of a program, built from exactly the ingredients we've been discussing all night. The router that forwards packets uses loops to check each incoming packet, and conditionals to decide which direction to send it. The TCP implementation uses variables to track which packets have arrived and which are still missing, loops to keep checking for new arrivals, functions to organize the complex logic of reassembly and retransmission. The messaging app itself uses all four of our core ideas: variables to hold the message text and the contact information, conditionals to decide whether to show a notification, loops to keep checking for new messages from the server, functions to handle all the different things a messaging app can do: sending, receiving, displaying, storing. And all of it runs on processors that have no idea what a message is, or what a friend is, or why it matters that these words arrived intact. They just fetch instructions, execute them, and move to the next, billions of times per second. The internet, the global network you use every day, is not a single thing. It's not owned by any one company or government. It's a vast, distributed, constantly growing collection of machines and connections and programs, all held together by these shared protocols, these agreed-upon rules for how to communicate. Any machine that follows the protocols can join the network. Any program that speaks TCP and IP can talk to any other program that speaks the same protocols, regardless of who made the machine, what operating system it runs, or where in the world it's located. This openness, this lack of central control, was a deliberate design choice by the early architects of the network, and it's one of the reasons the internet grew as quickly and as broadly as it did. There was no gatekeeper. If you could follow the rules, you could participate. This idea of programs talking to other programs across a network is not just a technical detail. It's the foundation of almost everything you use today. When you search for something on the web, your browser is sending a request to a server somewhere, which runs a program that searches through an enormous index and sends back a list of results. When you watch a video, your device is receiving a stream of packets from a server, reassembling them into video frames and displaying them on your screen, all in real time. When you check the weather, your phone is asking a server for the latest forecast data for your location. When you use a map, your device is constantly exchanging information with servers that know about road conditions and traffic and the best routes. Almost nothing on your phone happens in isolation anymore. Almost every app is a window onto a conversation between your device and servers somewhere else. Servers that might be in a data center a few miles away or on the other side of the planet, running programs that respond to your requests, store your data, and coordinate with other servers to provide whatever service you're using. And behind those servers, there are more servers, data centers full of them, rows and rows of machines, each running its own programs, talking to each other over internal networks, storing information, processing requests, backing up data. The scale is genuinely hard to hold in your mind. A single search query might touch hundreds or thousands of machines, each running its own small piece of the overall process, coordinating through protocols to return your results in less than a second. All of this, the entire stack from the smallest processor in your phone to the largest data center in the world, is built from the same fundamental pieces we've been exploring tonight: variables, conditionals, loops, functions, protocols. Programs running on processors that fetch and execute instructions, one at a time, without ever understanding what any of it means. The complexity is not in the pieces themselves. The pieces are simple, almost absurdly simple. The complexity is in the arrangement, the layering, the sheer number of pieces working together across time and space. It's the ant colony again, but now the colony spans the planet. Billions of simple instructions being executed every second by billions of processors, all coordinated through shared rules, producing behavior that looks, from a distance, like something intelligent, something purposeful, something aware. But it's not aware. None of it is. The router doesn't know it's routing your message to a friend. The server doesn't know it's storing your photograph. The processor in your phone doesn't know it's playing a voice that's helping you fall asleep. It's all just fetch and execute. Read an instruction, carry it out, move to the next. The meaning, the purpose, the warmth of a message from someone you love, the comfort of a familiar voice in the dark, all of that happens somewhere else. It happens in the minds of the people using the machines. The machines are carriers, conduits, faithful messengers that deliver the symbols without ever understanding what the symbols mean. That separation between the mechanical execution of instructions and the human meaning of the result is one of the quiet wonders of the modern world. It's also, in a way, the whole point. The machines do the mechanical work so that we don't have to. We get to live in the world of meaning, of connection, of understanding, while the machines live in the world of zeros and ones, of fetch and execute, of mindless, tireless, perfectly faithful repetition. Take a slow breath here. We've covered a great deal of ground. The history, from Jacquard's loom to Ada Lovelace's program to the stored program concept. The breakthrough of compilers, the bridge between human language and machine code. The four core ideas: variables, conditionals, loops, and functions. The mechanics of processors and the emergence of complexity from simplicity. The different styles of programming: procedural, object-oriented, functional, and now the network, the protocols, the global conversation of machines that makes your phone more than just a calculator, that makes it a window onto a connected world. If you're still with me, Let your mind rest on this image for a moment. Billions of tiny switches, flipping on and off, in patterns designed by millions of people across decades, all so that you, right now, can lie in the dark and hear a calm voice explaining how any of this came to be. The machines don't know they're doing it, but you know. And that knowing is something no program, no matter how sophisticated, can replicate. Now let's bring this back to where you are right now, tonight, because this is where all of it lives, quietly, around you, in your room. We've traveled a long way together, from a loom in France to a woman writing instructions for a machine that didn't exist. From rooms full of humming vacuum tubes to the stored program concept that made computers soft and changeable. From the first compilers that bridged human language and machine code to the four simple ideas that sit at the heart of every program ever written. We've talked about processors fetching and executing instructions billions of times per second, about the different styles programmers use to organize their thoughts, about protocols that let machines talk to each other across the planet. And now, after all of that, let's look around the room you're in, right now, and see where all of these ideas have quietly taken root. Think about your phone, resting somewhere nearby. Maybe it's on the nightstand, face down, its screen dark. Maybe it's on the bedside table, plugged into a charger, a small light glowing to show it's receiving power. Inside that device, at every moment, even while the screen is off, even while you're not touching it, dozens of programs are running simultaneously. Not one program, dozens. Each one built from exactly the ingredients we've described tonight. Variables and conditionals and loops and functions, all working together, all running on the same processor, sharing its time, taking turns, so fast that it feels like they're all running at once. There's a program monitoring the battery. It has a variable holding the current charge level, a number that changes slowly as the night goes on. It has a conditional checking whether the charge has dropped below a certain threshold, and if it has, it might trigger a notification, or adjust the screen brightness, or slow down certain background tasks to conserve power. It has a loop that checks the battery level again and again, many times per second, never getting bored, never forgetting to check, just doing its job, quietly, while you sleep. There's a program managing the wireless connections. It has variables holding the strength of the Wi-Fi signal, the name of the network you're connected to, whether Bluetooth is turned on or off. It has conditionals that decide what to do if the signal gets weak, whether to switch to a different network, whether to turn off Bluetooth to save power. It has loops constantly listening for incoming data, checking for new messages, new emails, new updates from apps that are running in the background. There's a program handling notifications. It has a list, a data structure, of every notification that's arrived since you last looked at the screen. It has conditionals deciding which notifications are important enough to light up the screen or make a sound, and which can wait quietly until morning. It has functions that format the notification text, that display the right icon, that group notifications from the same app together so they don't overwhelm you. There's a program rendering the screen. Even when the screen is off, it's still there, waiting. It has a loop that checks 60 times every second, or 120 times, depending on the device, whether anything has changed that requires updating the display. When you tap the screen, that loop catches the tap, records the position, and passes it to whatever program is responsible for responding to touches. All of this happens in less time than it takes for your finger to lift away from the glass. The processor inside your phone is reading instructions, one after another, billions of times each second, exactly as we described earlier. It has no imagination, no understanding, no sense of what a battery is, or a notification, or a message from someone you love. It just fetches the next instruction, executes it, moves to the next, over and over. But because it does this so fast, and because the instructions have been arranged so carefully by thousands of people across decades, the result is a device that feels responsive, attentive, almost thoughtful. It's not thoughtful, it's just fast and well-instructed. Think about the traffic lights outside, if you can picture the street near your home. At this hour, the traffic is probably light, maybe a single car every few minutes, headlights sweeping across the walls of your room. The traffic light at the intersection is running a program, a small, dedicated program, often quite simple, nothing like the complexity of a phone or a laptop. It cycles through a sequence, a loop. Wait a certain amount of time on red, then switch to green. Wait a certain amount of time on green, then switch to yellow. Wait a shorter amount of time on yellow, then switch back to red. Over and over, the same sequence, the same timing, all through the night. But many modern traffic lights have an extra layer, sensors buried in the road that detect whether a car is actually waiting. These sensors feed information into the program, a conditional. If a car is waiting on the side street and the main street has been green for a while, shorten the main street's green time and give the side street a turn. If no car is waiting, stay green on the main street. The program doesn't know what a car is. It doesn't know why people need to get home or why waiting at a red light with no cross traffic feels frustrating. It just checks a condition, compares a sensor reading against a threshold, and decides which path to follow. If this, then that. The same conditional we've been talking about all night, working quietly at an intersection near your home, keeping things moving safely while most of the city sleeps. Think about your refrigerator, if it's a newer one. Not the kind with a screen on the door, just an ordinary refrigerator with a thermostat inside. That thermostat is running a small program. It has a variable holding the current temperature inside the fridge. It has another variable holding the target temperature, the temperature you or the manufacturer set as the goal. It has a loop that checks the current temperature over and over, many times a minute. It has a conditional. If the current temperature is higher than the target temperature, turn on the compressor to start cooling. If the current temperature is at or below the target, turn the compressor off. Over and over, all through the night, a loop and a conditional working together, keeping your food at a steady, safe temperature without you ever having to think about it. These are not futuristic devices. They're ordinary. Traffic lights have been around for over a century. Refrigerators have been keeping food cold for generations. But the programs running inside them, the small, quiet, tireless sequences of instructions, are relatively new. They're part of a slow, steady migration of computation into the physical world, into everyday objects, into the background of life. This process has a name, the Internet of Things, though the name is less important than the reality it describes. The reality is that the ideas we've been exploring tonight, variables, conditionals, loops, functions, are no longer confined to the glowing rectangles we think of as computers. They've spread outward, into lights and locks and thermostats and cars and medical devices and industrial machinery and farm equipment and shipping containers and satellites. The physical world is increasingly animated by software, by instructions stored in memory, executed by processors that have no idea what they're controlling. And think about this very voice you're listening to right now. Somewhere, a program, built from exactly the same core ingredients we've spent the night exploring, took the words of this script, broke them into smaller pieces, analyzed the patterns of human speech, and generated the sound waves reaching your ears right now. This is a relatively new capability, this kind of generated voice. But underneath, it's the same story. A sequence of instructions, variables holding the text to be spoken, the pitch of the voice, the speed of delivery, conditionals deciding where to pause, where to rise, where to fall, loops processing one word after another, one sound after another, stitching them together into a continuous stream of speech. Functions organizing the complex process into manageable pieces, one function for analyzing the text, another for generating the sound, another for adjusting the rhythm, all of it running on a processor that doesn't know what a voice is, or what sleep is, or what it means to be tired and comforted by a calm explanation in the dark. The voice you're hearing right now is not a person, but it was made by people. People wrote the programs that generate it. People wrote the text it's reading. People, across decades, built the layers of technology that carry it from a server somewhere to the device in your room, through the protocols we talked about, through the routers and the data centers and the undersea cables. and people across nearly 2 centuries, starting with a woman writing instructions for a machine that didn't yet exist, developed the ideas that made all of it possible. The voice is not human, but it carries human intention, human care, human thought, transmitted through layers of mechanical execution that neither know nor care about the meaning they're carrying. This is the quiet strangeness of the world we've built. We are surrounded, at every moment, by processes that are mindless but not random, mechanical but not simple, tireless but not intelligent. The traffic light doesn't know it's keeping you safe. The refrigerator doesn't know it's keeping your food cold. The processor in your phone doesn't know it's delivering a message from someone you love. But they do these things anyway, faithfully, reliably, billions of times per second, because someone, somewhere, wrote a sequence of instructions that told them exactly what to do in every situation they would encounter. The intelligence is not in the machine. The intelligence was in the people who designed the machine, who wrote the program, who anticipated the situations and encoded the responses. The machine is just the executor, the faithful follower of instructions, the literal-minded assistant we've been imagining all night. Take a slow breath here. Let your attention rest on the objects around you. The phone, the clock, the speaker, the faint glow of a light somewhere in the room. Each of them, in its own way, is running programs. Each of them is following instructions. Each of them is part of the vast, distributed, layered system of computation that has grown up over the past 2 centuries, from that first loom in France to the global network that connects nearly every person on the planet. None of it was inevitable. None of it was obvious. It was built piece by people who saw a problem and imagined a solution, who took the ideas of those who came before and added their own layer, their own refinement, their own small contribution to the growing structure. And the structure is still growing. Right now, as you lie here, somewhere in the world, someone is writing a new program. Maybe it's a student, staying up late, working on their first real project, struggling with a loop that doesn't quite work the way they expect. Maybe it's a team of engineers, in an office on the other side of the planet, building the next version of an app you use every day. Maybe it's a researcher, experimenting with a new kind of program, one that learns from data in a way that earlier generations of programmers could barely have imagined. The work continues. The layers keep building. The ideas we've explored tonight, the loom, the cards, the stored program, the compiler, the 4 core ingredients, the protocols, they're not finished. They're still evolving, and the people building on them now are standing on the same foundation we've been tracing all night, the same foundation that Ada Lovelace helped lay, writing instructions for a machine that wouldn't exist for 100 years. If you're still awake, let your mind drift over this thought. The same ideas that animated Jacquard's loom are animating the device that's playing this voice. The same separation of plan from machine that Ada Lovelace understood is what lets you listen to this on a phone made by one company, running software written by another, connected to a network built by thousands of organizations cooperating through shared protocols. The same 4 ingredients, variables, conditionals, loops, functions, are what make your phone responsive, your traffic lights safe, your food cold, and your room filled with a calm voice explaining all of it to you. The pieces are simple, the arrangements are complex, the result is the world you live in, right now, tonight. Let's turn gently now to the harder questions, the parts of this subject that remain strange or unresolved, even to the people who understand it best. We've spent the night building up a picture of programming, layer by layer, from the loom to the compiler to the 4 core ideas to the global network. And that picture, if we stopped here, might seem complete. It might seem like a story of steady, cumulative progress, each generation adding its layer, each problem finding its solution, until we arrived at the world we have today, with its glowing rectangles and its traffic lights and its calm voices in the dark. But there are corners of this subject that don't fit neatly into a story of progress. There are questions that have been asked and answered, and the answers have turned out to be stranger and more humbling than anyone expected. Let's sit with a few of those tonight, not because you need to understand them fully, but because acknowledging the limits of a subject is often the deepest way of understanding it. Here's one that has puzzled computer scientists since the very beginning of the field. Before there were computers, before there were electronic circuits, back when computation was still an idea being worked out on paper by mathematicians trying to understand what could and could not be calculated. The question is this: can you write a program whose job is to look at any other program and any input you might give that program and correctly determine, in advance, whether that program will eventually finish running and produce an answer, or whether it will get stuck, running forever, never reaching a conclusion? This is called the halting problem, and it was proven by Alan Turing himself back in 1936, before electronic computers existed, that the answer is no. Not, we haven't figured out how yet. Not, it's very difficult and no one has solved it. The answer is that it's provably, mathematically impossible for any single program to correctly answer this question for every possible other program. There will always be some program, some input, some situation, where the checking program simply cannot know the answer in advance. Let's sit with what this means, because it's subtle. It doesn't mean that we can't tell whether some specific programs will halt. We can. If you write a simple program that counts from 1 to 10 and then stops, it's easy to see that it will halt. If you write a program that loops forever, counting up from 1 and never stopping, it's easy to see that it won't halt. The halting problem doesn't say that we can never know. It says that there is no single, universal method, no one program, that can correctly decide the question for every possible program. There will always be some programs that defeat any given method, some programs that are too tangled, too self-referential, too clever by half, for any general-purpose checker to figure out. Turing proved this using a kind of argument that has become famous in computer science, an argument by contradiction that goes something like this. Suppose there were a program that could solve the halting problem. Call it the halting checker. You give it another program and an input, and it tells you, yes, this program will eventually halt, or no, it will run forever. Now, using this halting checker, you could build a mischievous program, a program designed specifically to confuse the checker. This mischievous program would ask the checker about itself. If the checker said it would halt, the mischievous program would deliberately loop forever. If the checker said it would loop forever, the mischievous program would immediately halt. Either way, the checker would be wrong. And since the mischievous program was built using the checker itself, the only conclusion is that a perfect halting checker cannot exist. The very idea of it leads to a contradiction. This is a strange, humbling limit, found through pure logic, sitting at the very foundation of what computation can and cannot do. No matter how powerful our machines become, no matter how clever our programmers get, there are questions about programs that no program can ever answer in full generality. There are limits to what can be computed. There are edges to the world of software, and we can prove, with mathematical certainty, that those edges exist. This matters, practically, in subtle ways. It means that there is no automatic tool that can look at any program and guarantee that it's free of infinite loops. It means that there's no perfect antivirus that can examine any piece of code and determine, with certainty, whether it's malicious or safe. It means that writing correct software will always, at some level, require human judgment, human care, human attention to detail that cannot be fully automated away. The halting problem is a reminder that computation, for all its power, has boundaries. There are things it simply cannot do, and those boundaries were mapped not by running experiments, but by thinking carefully, by reasoning about the nature of instructions and machines and what it means to follow a sequence of steps. Here's another strange corner. Programs, despite being built from such simple, mechanical pieces, individual instructions, followed exactly, without any understanding or creativity, can still contain mistakes so subtle that they go unnoticed for years, sometimes decades. These mistakes hide inside otherwise perfectly functioning software, waiting for one very particular, very unusual combination of conditions to reveal them. The program works correctly almost all the time. It passes all the tests. It does what it's supposed to do, day after day, year after year. And then, one day, the conditions align just so, a specific input arrives, a specific sequence of events unfolds, and the mistake surfaces. The program does the wrong thing. Sometimes in a small way, a display glitch, a number that's slightly off. Sometimes in a large way, a system crash, a security breach, a spacecraft going off course. These mistakes are called bugs. The term is old, older than electronic computers. Engineers in the 19th century used it to describe flaws in mechanical systems, things that didn't work quite right for reasons that were hard to track down. But the term became permanently attached to computing in 1947, when Grace Hopper's team, working on an early computer at Harvard, found an actual moth stuck inside one of the relays, the electromechanical switches that made the machine work. The moth had been drawn to the warmth or the light, or perhaps just wandered in by accident, and its body was preventing the relay from closing properly. The team removed the moth with tweezers and taped it into their logbook with the note, "First actual case of a bug being found." The logbook still exists. The moth is still there, a small brown smudge on a page of notes about voltages and circuits. The story is charming, and it's often told as a kind of origin myth. But the deeper point is what happened next. The term bug stuck, and debugging became the word for the process of finding and fixing errors in software. Because errors are everywhere. Every programmer spends a great deal of their time debugging. Writing the code is often the quick part. Finding out why it doesn't quite work, why it works in most cases but not in this one, why it crashes when you do this specific unusual thing, that can take hours or days or longer. And the reason is that programs, even though they're built from simple pieces, become complex very quickly. The number of possible paths through a program, the number of different combinations of inputs and conditions and states, grows faster than a human mind can track. A program with a few hundred lines of code might have more possible execution paths than there are stars in the galaxy. Testing every single one is impossible. So programmers test the most likely ones, the most common ones, the ones that seem risky, and they rely on careful design and experience and tools to catch the rest. But some always slip through. Some bugs are famous. In the 1990s, a bug in the software controlling a European rocket called Ariane 5 caused the rocket to veer off course and self-destruct less than a minute after launch. The bug was in a piece of code that had been reused from an earlier rocket, the Ariane 4, where it had worked perfectly for years. But the Ariane 5 was faster, and the code wasn't designed to handle the larger numbers that came with the higher speed. A number got too big for its container, an overflow error, and the guidance system failed. The rocket, along with the scientific satellites it was carrying, was destroyed. All because of a few lines of code that hadn't been updated for new conditions. Other bugs are quieter. They sit in software for years, unnoticed, until someone with the right skills and the wrong intentions finds them. Security vulnerabilities, they're often called. They're bugs that don't cause crashes or obvious errors, but instead open doors that were meant to be closed. A carefully crafted input can trick the program into revealing information it shouldn't, or into running instructions it wasn't supposed to run. The program, being literal-minded, doesn't know it's being tricked. It just follows the instructions it's given, exactly as it always does, and the result is a breach of security that the original programmer never imagined. The existence of bugs is not a sign that programmers are careless. It's a sign that programming, at its core, is a human activity. Humans are fallible. Humans cannot hold the full complexity of a large system in their heads all at once. Humans make mistakes, and the machines, for all their speed and precision, cannot save us from those mistakes. They can only execute them, faithfully, at billions of steps per second. Debugging is the process of finding the gap between what the programmer intended and what the instructions actually say. And that gap can be very small, a single wrong number, a condition that checks for the wrong thing, a loop that runs one time too many or one time too few, and the consequences can be very large. And here's a question that reaches right into tonight, into this very moment, into the voice you're hearing and the way it was made. In recent years, a new kind of program has emerged, one that doesn't follow a fixed sequence of instructions written directly by a programmer. Instead, these programs learn patterns from enormous amounts of information, adjusting their own internal structure gradually, through a process built on very old ideas, statistics, probability, the mathematics of optimization, and something called neural networks, loosely inspired by the way neurons connect in a brain, though far simpler and quite different underneath. The way these programs are built is not by writing instructions that say, do this, then do that, then check this condition. Instead, you show the program a vast number of examples, millions of photographs labeled with what they show, millions of sentences paired with translations into another language, millions of audio recordings paired with their transcripts, and the program adjusts its internal parameters, its own kind of variables, bit by bit, until it becomes good at the task, good at recognizing faces, good at translating languages, good at generating speech from text. The program learns, but not in the way a person learns. It learns statistically, by finding patterns in the data, by minimizing errors through a process of gradual adjustment that no human directly controls. The result is software that can do things that would be impossible to write as a fixed sequence of rules. Generating natural-sounding speech, like the voice you're hearing now. Recognizing objects in photographs, even in bad lighting, even from strange angles. Holding something that feels like a conversation, though it's important to understand that it doesn't know what it's saying. It's predicting, based on patterns in the data it was trained on, what words are most likely to follow the words that came before. It's following statistical rules, not understanding meaning. It has no idea what a conversation is, or what it's like to be a person, or what any of its words refer to in the real world. It's pattern matching at an enormous scale, and yet, underneath all of it, at the very bottom, it's still the same fundamental ingredients we've spent tonight exploring. Instructions, read one at a time, by a processor with no understanding at all. Variables, holding the enormous matrices of numbers that represent the network's learned parameters. Loops, iterating over the training data, adjusting those numbers bit by bit. Conditionals, deciding when to stop training, when to apply this adjustment rather than that one. Functions, organizing the complex mathematics into manageable pieces. The new kind of program is not made of different pieces, it's made of the same pieces, arranged in a different way, at a different scale, with the content of the program coming not from a programmer's explicit design, but from the patterns implicit in the data. This is a significant shift in how software is built, and it's still unfolding, still being understood, still raising questions that don't have settled answers. What does it mean for a program to behave in ways that even its creators can't fully predict or explain? How do we test software that learned its behavior from data rather than having it specified in rules? What happens when these systems are used to make decisions that affect people's lives, decisions about loans or hiring or medical treatment, and we can't easily explain how the system arrived at its conclusion? These are not questions with simple answers. They're questions that the field is wrestling with right now, tonight, while you lie here listening. But here's what hasn't changed. The processor running these new kinds of programs is the same processor we've been talking about all night. It fetches an instruction, executes it, moves to the next. It doesn't know if the instruction is part of a traditional program or a learned model. It doesn't know if the behavior it's producing is understandable or mysterious. It just follows the sequence, billions of times per second, the same way it always has. The fundamental nature of computation hasn't changed. What's changed is how we, the humans, create the sequences that the processor follows. We've moved, in some cases, from writing the rules ourselves to building systems that derive their own rules from data. But the rules, once derived, are still just instructions, still variables and conditionals and loops and functions, still executed step by a machine that has no idea what any of it means. This is where the story of programming has arrived, at least for now. A field that began with a woman writing instructions for a machine that didn't exist has grown into systems that write their own instructions, in a sense, though not with intention or understanding, just with statistics and optimization. The scale and the methods have changed, the fundamental pieces have not. And the fundamental separation between the mechanical execution of instructions and the human meaning of the result remains as wide as it was when Ada Lovelace first saw that a machine following rules could operate on symbols that represented more than just numbers. The machine still doesn't know what it's doing. The meaning still lives somewhere else. It lives in the people who build the machines, in the people who train the models, in the people who use the software, in the people who listen to voices in the dark and feel, despite knowing better, that someone is there, someone who understands. By now you may have drifted in and out a few times. That's exactly right. There's nothing to catch up on, nothing you've missed that you need to go back and find. Everything has been settling quietly, whether you were following closely or not, the way a room slowly grows warmer, without you noticing the exact moment it happened. The ideas have been here, in the air around you, and some of them have landed, and some of them have passed by, and either way, that's fine. That's how this is meant to work. Let's bring everything together now, gently, into one picture, because that's what tonight has really been building toward. Not a collection of facts, not a list of dates and names to memorize, but a single, clear image that you can hold in your mind, that you can return to on other nights, that can sit quietly in the background of your understanding from now on. If you were to hold all of tonight in one image, it would be this: a very obedient, very literal-minded assistant, infinitely patient, incapable of boredom or distraction, capable of following instructions with perfect, tireless precision, but with no imagination, no understanding, no sense of meaning at all on its own. It cannot guess what you meant to say. It cannot notice if something seems wrong. It cannot step back and consider the bigger picture. It can only do exactly what it's told, in the exact order it's told to do it, without ever stopping to ask why. This assistant has no physical form. It's not a robot. It's not a character. It's more like a principle, a force, a capacity for following instructions that sits at the heart of every computing device ever made. The processor in your phone is this assistant. The microcontroller in your refrigerator is this assistant. The server in a data center on the other side of the world is this assistant. They are all, at bottom, the same thing. A mechanism for reading instructions, one at a time, and carrying them out, without ever understanding what those instructions are for, or what they mean, or why they matter. Humans, across nearly 2 centuries now, starting with a woman writing instructions for a machine that didn't yet exist, have found ways to speak to this assistant. At first, the speaking was physical. Patterns of holes punched into cards, like the ones Jacquard used for his loom, like the ones Babbage imagined controlling his analytical engine, like the ones Ada Lovelace used to write what many consider the first computer program. The instructions were tangible. You could hold them in your hand. You could see the holes. You could store the cards on a shelf and bring them back out when you needed that particular pattern again. Then, as the machines became electronic, the speaking became numerical. Raw sequences of numbers, expressed in binary, zeros and ones, that corresponded directly to the operations the hardware could perform. Writing in machine code meant speaking the machine's own language, thinking in the machine's own terms, holding long strings of digits in your head. It was exact but exhausting, and a single wrong digit could unravel everything. Then came the translators, the compilers. Grace Hopper's idea, so simple in retrospect, so transformative in its moment. Write a program whose job is to translate readable words, words closer to human language, into the numerical sequences the machine needs. Let the programmer write add instead of a string of binary digits. Let the programmer think about the problem, the calculation, the task, while the compiler handles the tedious work of turning intention into instruction. This was the moment programming moved up a level, away from the raw hardware, towards something a human mind could hold onto more comfortably. It was the building of a bridge between the world of human thought and the world of machine execution. And from that bridge the ideas grew. Variables, small labeled boxes that can hold different values at different times. Conditionals, the ability to make decisions, to check something and choose between two paths. Loops, the ability to repeat something without writing it out again and again, to count from 1 to 1,000,000 without typing 1,000,000 separate lines. Functions, the ability to give a name to a reusable sequence of steps so that complex programs can be built from smaller, well-understood pieces, the way a car is built from an engine and a transmission and wheels, each designed somewhat separately, each connected through agreed-upon interfaces. These 4 ideas, so simple they can be explained to a 5-year-old, are the foundation of everything. Every app on your phone, every website you visit, every traffic light, every thermostat, every voice in the dark. They are all, at bottom, arrangements of variables and conditionals and loops and functions, translated by compilers or interpreters into machine instructions, executed by processors that fetch and carry out one instruction after another, billions of times per second, without ever knowing what any of it means. And then, on top of that foundation, the layers kept building. Different styles of organizing code, procedural and object-oriented and functional, different philosophies for managing complexity as programs grew larger and more interconnected, protocols for communication, agreed-upon rules that let machines built by different companies, running different software, in different countries, exchange information reliably across imperfect networks. The Internet, that vast, distributed, constantly growing web of connections, built on top of simple protocols like TCP and IP, which handle the unglamorous but essential work of breaking messages into packets, addressing them correctly, and reassembling them on the other end, even if some packets get lost or arrive out of order. And all of this, the entire immense structure, from the smallest embedded processor in a traffic light to the largest data center housing millions of servers, is still, at its core, the same thing it's always been. Instructions, stored in memory, read one at a time, executed faithfully, by a machine that has no idea what it's doing. The scale has changed, the speed has changed, the complexity of the arrangements has changed, but the fundamental nature of computation has not. It's still the literal-minded assistant, following a list of steps, doing exactly what it's told, without ever understanding why. And from these humble ingredients humanity has built, piece by piece, layer upon layer, across generations of programmers standing on each other's work, everything from the traffic lights outside your window, to the voice reading you to sleep right now, to systems vast enough to model the entire Earth's weather, to networks that connect nearly every person on the planet into a single, continuous conversation. The same ideas that animated a loom in France in 1801 are animating the device on your nightstand right now. The same separation of plan from machine that Ada Lovelace perceived is what lets you listen to this recording on a phone made by one company, running software written by another, connected to a network maintained by thousands of organizations, all because they agreed on shared protocols and shared principles. This is the picture, the patient, mindless assistant, the humans, across 2 centuries finding better and better ways to speak to it, the layers of translation and organization that let human intention reach down into the world of electrical switches and binary patterns. The simple pieces, variables, conditionals, loops, functions that combine and recombine into structures of immense complexity. And the curious fact, the fact that sits at the center of the whole story, that none of it understands what it's doing. Not really. Not the way you understand things, lying here in the quiet of your own room. The processor executing this very sentence's audio doesn't know what a sentence is. It doesn't know what sleep is, or what it means to be tired, or why a calm voice in the dark can be comforting. It simply follows instructions exactly, endlessly, the way it always has. The way Jacquard's loom followed the pattern of holes, lifting a thread where there was a hole, keeping it down where there wasn't, never knowing it was weaving roses into silk. The way Babbage's engine, had it ever been built, would have followed Ada's careful list of steps, performing the calculations she specified, never knowing that one day people would look back at her notes and see the first program ever written. The way the early electronic computers followed their stored programs, reading numbers from memory, treating some as commands and some as data, never knowing whether they were calculating artillery trajectories or processing census results or helping to land a spacecraft on another world. The understanding, the meaning, the warmth, all of that lives somewhere else. It lives in you. It lives in the people who wrote the programs, in the people who designed the protocols, in the people who built the devices, in the people who use the software, who send the messages, who take the photographs, who listen to the voices in the dark. The machines carry the symbols. They transmit the patterns. They execute the instructions with perfect, tireless fidelity. But they don't know what any of it means. They can't. They were never built to. That was never their job. Their job was to follow the steps, to flip the switches, to fetch and execute, over and over, so that we, the humans, could get on with the business of meaning, of connection, of understanding, of rest. This separation between mechanical execution and human meaning is not a flaw. It's not something we're waiting to solve. It's the whole point. It's what makes the entire enterprise work. The machines do the part of the work that can be reduced to exact, unambiguous steps. The part that requires patience, precision, and speed that no human could match. And we do the part that requires judgment, creativity, care, and the kind of understanding that comes from being alive, from having a body, from knowing what it's like to be tired at the end of a long day, to find comfort in a familiar voice, to drift towards sleep with the quiet sense that someone, somewhere, thought about you long enough to write this, to record this, to send this out into the night. So let it go now, whatever's left of tonight's attention. You've traveled a long way, from a loom in France to the processor in your phone, from the first compilers to the global internet, from the halting problem to the bugs that hide in software for decades. You've sat with the 4 core ideas that underpin everything, and you've seen how they combine and recombine into structures of immense complexity. You've heard about the limits of computation, the things that no program can ever do, and about the new kinds of programs that learn from data rather than following fixed rules. And through all of it, you've held on to the central image, the patient, literal-minded assistant, following instructions it doesn't understand, so that you can live in a world full of meaning that it cannot share. If some of this stays with you, good. If most of it fades, that's good too. Understanding doesn't always mean remembering every detail. Sometimes it just means having a sense of how something works, a framework that the details can hang on if they ever come back. You now have that framework. You know what a program is, at its core. You know how someone builds one, at least in principle. You know why this strange invention has rearranged so much of the world, and why, despite all of that rearranging, the fundamental nature of the machine has stayed the same. It follows instructions. We give them meaning. That's the whole story, and it's enough. So, let it go now, whatever's left of tonight's attention. You've been listening for a while, and whether you've caught every word or drifted in and out, you've absorbed more than you probably realize. The mind has a way of holding on to the shape of an idea, even when it can't recall every detail. The framework is there now. The picture is in place. And the rest can fade, the way the details of a dream fade after you wake up, leaving only the feeling, the sense that something was understood, even if you can't quite say what. Somewhere near you, quietly, in the dark, small processors are still working, exactly as they have been this whole time. They don't know you're falling asleep. They don't know you exist. They don't know anything. They are patient, tireless, following their instructions without ever needing rest, without ever wanting rest, without ever knowing what rest means. The processor in your phone is still fetching instructions, executing them, moving to the next. The microcontroller in your refrigerator is still checking the temperature, comparing it to the target, deciding whether to turn the compressor on or off. The traffic light at the intersection near your home is still cycling through its sequence, red to green to yellow to red, checking its sensors, making its simple decisions over and over through the quiet hours of the night. These machines don't need you to watch over them. They don't need you to understand them. They were designed to work without attention, without appreciation, without anyone even knowing they're there. That's part of what makes them so useful. They fade into the background. They become part of the texture of everyday life, like the hum of a refrigerator or the faint glow of a clock on the nightstand. You don't have to think about them. You don't have to keep up with them. You were never really built to run the way they do. You were never built to run the way they do. That's worth sitting with for a moment, because it's easy to forget. The machines we've been talking about all night, the processors and the programs and the protocols, they operate on a time scale that has nothing to do with human life. They count in billionths of a second. They execute millions of instructions in the time it takes you to draw a single breath. They never get tired. They never lose focus. They never need to stop and rest and let their minds go blank. They can sustain perfect, unwavering attention on a single task for hours, for days, for years, without ever slipping, without ever wanting to do something else. You are not like that. You were never meant to be like that. You were built for something different. You were built to drift, to forget, to dream, to rest. Your attention is not a steady beam that can stay fixed on one point forever. It's more like a tide, rising and falling, coming in and going out. Sometimes you're fully present, catching every word, following every thread. Sometimes you're somewhere else, your mind wandering to something that happened earlier in the day, or something that might happen tomorrow, or nothing at all. Just a soft, comfortable blankness. That's not a flaw. That's not a failure of concentration. That's how human minds work. That's how they've always worked. And no amount of technology, no matter how sophisticated, will change that fundamental fact. The machines can imitate attention. They can seem attentive. The voice you're hearing right now sounds like someone paying careful attention to every word, modulating every phrase, pausing in the right places. But it's not. It's a program, following instructions, generating sound waves from text, without ever knowing what attention means, or what it's like to give attention to something, or what it's like to have your attention drift away and then come back. The machine doesn't drift. The machine doesn't dream. The machine doesn't rest. Those are human things. They belong to you. So let the machines do what they do. Let them count their billions of instructions. Let them cycle through their loops. Let them check their sensors and make their decisions and send their packets across the network. They don't need your help. They don't need your supervision. They were built to run on their own in the background while you get on with the human business of sleeping and dreaming and waking up to a new day. You don't have to count with them. You don't have to keep pace. The number they're counting toward, whatever it is, 1 million, 1 billion, some threshold that will trigger the next step in their program, they will reach it in their own time, at their own speed, without any effort on your part. They were designed to count. You were not. You were designed for other things, for rest, for renewal, for the slow, quiet processes that happen in the dark, when your conscious mind lets go and your body gets on with the work of repairing itself, consolidating memories, restoring energy for the day ahead. Let the room stay quiet now. Let the small lights blink on, unnoticed, doing their work without you. The light on your phone charger, the light on your router, the light on the smoke detector on the ceiling, blinking once every minute or so, just to let you know it's still working. Each of those lights is connected to a program, a small sequence of instructions that tells it when to turn on and when to turn off. Each of those programs was written by someone, somewhere, who thought about what that light should do and wrote the code to make it happen. And now those programs run, silently, tirelessly, without anyone watching, without anyone thinking about them, keeping their small part of the world in order while the larger world sleeps. There's something peaceful about that, if you let yourself feel it. The idea that while you rest, an entire invisible infrastructure continues to hum along, quietly, reliably, keeping things running until you wake up. The messages that arrive overnight will be stored, waiting for you. The alarm you set will go off at the right time, because a program is keeping track of the hours and minutes, checking over and over whether it's time to sound the alarm. The house will stay warm or cool because a thermostat somewhere is running its loop, checking the temperature, making its decisions. None of this requires your attention. None of this requires your effort. It's all being handled by machines and programs and protocols while you let go. Somewhere, a program is still counting, patiently, towards some number it will never mind reaching. It doesn't know what the number means. It doesn't care, it just counts. One instruction after another, one cycle after another. Fetch, execute, move to the next. The number itself is irrelevant. The counting is the point. The counting is what it does. And when it reaches that number, whatever it is, it will do whatever the next instruction tells it to do. Maybe it will start over. Maybe it will send a signal. Maybe it will stop and wait for something else to happen. It doesn't matter. What matters is that it keeps going, reliably, without complaint, without fatigue, while you do something it can never do, while you rest. You don't have to count with it. That's the line to hold on to as you drift. You don't have to count with it. You don't have to keep up. You don't have to match its pace or its precision or its tirelessness. You are not a machine. You are not a processor. You are not a program, following a fixed sequence of steps, over and over, without variation, without rest. You are something else entirely. Something that needs sleep. Something that needs dreams. Something that needs to let go of the day and sink into the quiet dark, trusting that the machines will keep their watch, that the programs will keep running, that the world will still be there when you wake up. The machines don't mind that you're leaving them. They don't know you're leaving. They don't know you were ever here. They just continue, as they always have, as they were designed to do. The traffic lights keep cycling. The refrigerator keeps cooling. The phone keeps listening for messages. The network keeps routing packets. The whole vast, layered system of computation that we've explored tonight keeps running, silently, in the background, while you close your eyes and let your breathing slow and allow yourself to drift away from the world of instructions and processors and protocols into the world of rest. That's the bargain, if you want to think of it that way. The machines do the work they were built to do. They follow the instructions they were given. They execute the programs, fetch and execute, over and over, without ever understanding what any of it means. And we, the humans, get to do what we were built to do. We get to live in the world of meaning. We get to care about things and love people and feel tired at the end of a long day and find comfort in a calm voice in the dark. We get to rest. The machines don't get to rest, but they don't need to. Rest is for the living. Rest is for those who understand, somewhere deep in their bodies, that activity and stillness are both necessary, that the tide goes out as well as in, that sleep is not a waste of time, but a kind of renewal that no machine, no matter how sophisticated, can replicate. So let yourself sink now. Let the pillow take the weight of your head. Let the blanket settle around your shoulders. Let your breathing find its own rhythm, slow and steady, without you having to direct it. The room is quiet. The machines are working. Everything is as it should be. And somewhere, in the dark, a small processor is still counting, patiently, toward a number it will never mind reaching. You don't have to count with it. You don't have to wait for it to finish. You don't have to do anything at all except rest. Let the room stay quiet now. Let the small lights blink on, unnoticed, doing their work without you. You've been listening for a while, and the night has grown deeper around you. The house has settled. The street outside has gone still. The only movement now is the gentle rise and fall of your own breathing and the silent, invisible work of the machines that surround you, keeping their quiet vigil while you rest. There's something worth noticing in this moment, something that's easy to overlook when you're awake and busy and moving through the day. Right now, in the dark, you are not alone. Not in the sense that there's someone else in the room. There isn't. But you are surrounded by evidence of other minds, other people's thoughts, other people's care. The program running on your phone was written by someone. The protocols that carry this voice to your ears were designed by someone. The text being spoken was composed by someone, sitting somewhere, thinking about you, or thinking about someone like you, someone lying in the dark, wanting to understand, wanting to rest. This is the part of the story that's easy to miss when we focus only on the machinery. The processors and the memory and the fiber optic cables, those are the how. They explain how the voice reaches you, how the message arrives, how the traffic light changes from red to green. But they don't explain the why. The why comes from people. People who had a problem to solve, or an idea to express, or a gift to give. People who sat down at some point and wrote a sequence of instructions, not because they had to, but because they wanted to make something, build something, share something. Every program, no matter how simple or how complex, began as an act of human intention. Someone, somewhere, decided that something should happen and wrote down the steps to make it happen. The machines don't know this. They don't know that they're carrying someone's intention. They don't know that the program they're running was written by a person who stayed up late, or woke up early, or spent weeks chasing down a bug that only appeared under the most unusual conditions. They don't know that the protocol they're following was debated, refined, argued over by committees of engineers who cared deeply about getting it right. They don't know that the voice they're producing was recorded or generated by someone who wanted it to sound calm, warm, gentle enough to help a stranger fall asleep. But you can know this. You can lie here in the dark and feel, if you let yourself, the presence of all those other minds, all those other intentions, layered into the devices and the networks and the software that surround you. It's a strange kind of connection, indirect and mediated by machines, but it's real. The person who wrote the code for your phone's alarm clock thought about you, in a way. They thought about the kind of person who needs to wake up at a certain time, who sets an alarm before going to sleep, who trusts that the alarm will sound when it's supposed to. They built something to serve that need, and now, tonight, that something is running, quietly, reliably, waiting for the moment when it will do its job. The person who designed the traffic light program thought about you too. They thought about the drivers and the pedestrians and the cyclists, all the people moving through the intersections, each with their own destinations, their own schedules, their own reasons for being out in the world. They built something to keep those people safe, to keep the flow of traffic moving smoothly, to reduce the chance of collisions and confusion. And tonight, while the streets are mostly empty, that program is still running, still checking its sensors, still making its decisions, because the person who wrote it didn't know exactly when it would be needed, so they made it ready at all times. Even this voice, the one you're hearing right now, carries the imprint of human intention. Someone wrote these words. Someone chose the pacing, the tone, the rhythm. Someone decided that there should be a thing in the world that explains programming, slowly and gently, to people who are trying to fall asleep. That decision, that intention, is what set everything in motion. The machines just carried it out. This is worth holding on to as you drift. The machines are faithful messengers, but they are only messengers. The meaning they carry comes from elsewhere. It comes from people, from their ideas and their efforts and their care. And that means that when you use a device, when you open an app, when you listen to a voice in the dark, you are, in a small but real way, in contact with the people who made it. Not directly, not in a way they'll ever know about, but the connection is there, a thread of intention running from their mind to yours, through layers of code and hardware and network protocols, all of it designed to carry meaning faithfully from one person to another. The machines don't understand this connection. They don't need to. They just need to follow their instructions, fetch and execute over and over, while the meaning flows through them like water through a pipe. The pipe doesn't know it's carrying water, it's just a pipe. But without the pipe, the water wouldn't reach its destination. The machines are the pipes. We are the water. We are the meaning. We always have been. So let the machines keep doing what they do. Let them keep counting, keep checking, keep routing packets and cycling through loops. They're good at it. They were built for it. And while they work, let yourself rest in the knowledge that you are connected, even now, even in the dark, to a vast network of human effort and human care. The person who wrote the program that plays this voice. The person who designed the compression algorithm that makes the audio small enough to stream. The person who laid the fiber optic cable that carries the data to your device. The person who assembled the phone on your nightstand. None of them know you personally, but they built something for you anyway. They built something for the person who would use it, whoever that turned out to be. And you, right now, are that person. You are the one the programs were written for. The alarm was set for you. The traffic light will change for you, or for someone like you, someone trying to get home safely. The voice is speaking to you. Not to a generic audience, but to you, the specific person lying in this specific room, in this specific moment, listening. That's the quiet truth at the heart of all of this. The machines don't care about you. They can't. But the people who built the machines, who wrote the software, who designed the protocols, they did care. They built all of this so that it would work for someone. And tonight, that someone is you. Let that thought settle. Let it be a small warmth in the dark. You are not alone. You are surrounded by the results of human effort, human ingenuity, human care. The machines are just the delivery system. The gift itself comes from other people, from thousands of them, tens of thousands, across decades, across continents, each one adding their small contribution to the growing structure. Ada Lovelace, writing instructions for a machine that didn't exist. Grace Hopper, building the first compiler so that programmers could write in words instead of numbers. Vint Cerf and Robert Kahn, designing protocols so that machines could talk to each other across any distance. And all the others, the ones whose names you'll never know, who wrote the code for your phone's operating system, who tested the firmware for your router, who debugged the software that generates synthetic speech. All of them, in their own way, built something for you. The machines will keep working through the night. They don't need your gratitude. They don't need anything. But perhaps, as you drift towards sleep, you can feel a quiet sense of appreciation, not for the machines themselves, but for the human hands and minds that shape them. For the fact that you live in a world where so many people, most of whom you'll never meet, have built things to make your life a little easier, a little safer, a little more connected. The alarm will wake you in the morning. The traffic light will help you get where you're going. The voice will fade into silence when the recording ends, having done what it was meant to do. And somewhere, a program is still counting, patiently, toward some number it will never mind reaching. It doesn't know why it's counting. It doesn't need to know. The counting was someone's idea, someone's intention, set in motion long ago, and now it continues, on its own, while the person who started it sleeps, or works, or has long since moved on to other projects. The program doesn't remember its creator, but the creator's intention is still there, embedded in the code, carried forward in time by a machine that never forgets, never tires, never stops until it's told to stop. You don't have to count with it. You don't have to match its pace or its persistence. You are not a machine. You are the reason the machine exists. You are the point. Without you, without the person on the other end, all of this would be meaningless. The programs would still run. The processors would still fetch and execute. The packets would still travel across the network. But there would be no one to benefit from it, no one to read the message or hear the voice or wake up to the alarm. The machines need us to complete them. Without us, they're just patterns of electricity, running in empty loops, serving no purpose. With us, they become something more. They become carriers of meaning, of connection, of care. So rest now, in the knowledge that you matter to all of this. Not because you built it, but because you're the reason it was built. The machines are working for you tonight. Let them. They don't mind. They don't know what minding would even mean. They just do what they were told, faithfully, tirelessly, while you close your eyes and let the day fall away. The room is quiet. The lights are blinking, on and off, in patterns designed long before tonight. Everything is working as it should. And you, the person all of this was built for, can finally let go. Let the room stay quiet now. Let the small lights blink on, unnoticed, doing their work without you. You've been listening for a while, and the night has grown deeper around you. The house has settled. The street outside has gone still. The only movement now is the gentle rise and fall of your own breathing and the silent, invisible work of the machines that surround you, keeping their quiet vigil while you rest. There's something worth noticing in this moment, something that's easy to overlook when you're awake and busy and moving through the day. Right now, in the dark, you are not alone, not in the sense that there's someone else in the room. There isn't, but you are surrounded by evidence of other minds, other people's thoughts, other people's care. The program running on your phone was written by someone. The protocols that carry this voice to your ears were designed by someone. The text being spoken was composed by someone, sitting somewhere, thinking about you, or thinking about someone like you, someone lying in the dark, wanting to understand, wanting to rest. This is the part of the story that's easy to miss when we focus only on the machinery, the processors and the memory and the fiber optic cables. Those are the how. They explain how the voice reaches you, how the message arrives, how the traffic light changes from red to green. But they don't explain the why. The why comes from people. People who had a problem to solve, or an idea to express, or a gift to give. People who sat down, at some point, and wrote a sequence of instructions, not because they had to, but because they wanted to make something, build something, share something. Every program, no matter how simple or how complex, began as an act of human intention. Someone, somewhere, decided that something should happen and wrote down the steps to make it happen. The machines don't know this. They don't know that they're carrying someone's intention. They don't know that the program they're running was written by a person who stayed up late, or woke up early, or spent weeks chasing down a bug that only appeared under the most unusual conditions. They don't know that the protocol they're following was debated, refined, argued over by committees of engineers who cared deeply about getting it right. They don't know that the voice they're producing was recorded or generated by someone who wanted it to sound calm, warm, gentle enough to help a stranger fall asleep. But you can know this. You can lie here in the dark and feel, if you let yourself, the presence of all those other minds, all those other intentions, layered into the devices and the networks and the software that surround you. It's a strange kind of connection, indirect and mediated by machines, but it's real. The person who wrote the code for your phone's alarm clock thought about you, in a way. They thought about the kind of person who needs to wake up at a certain time, who sets an alarm before going to sleep, who trusts that the alarm will sound when it's supposed to. They built something to serve that need, and now, tonight, that something is running, quietly, reliably, waiting for the moment when it will do its job. The person who designed the traffic light program thought about you too. They thought about the drivers and the pedestrians and the cyclists, all the people moving through the intersections, each with their own destinations, their own schedules, their own reasons for being out in the world. They built something to keep those people safe, to keep the flow of traffic moving smoothly, to reduce the chance of collisions and confusion. And tonight, while the streets are mostly empty, that program is still running, still checking its sensors, still making its decisions, because the person who wrote it didn't know exactly when it would be needed, so they made it ready at all times. Even this voice, the one you're hearing right now, carries the imprint of human intention. Someone wrote these words. Someone chose the pacing, the tone, the rhythm. Someone decided that there should be a thing in the world that explains programming, slowly and gently, to people who are trying to fall asleep. That decision, that intention, is what set everything in motion. The machines just carried it out. This is worth holding on to as you drift. The machines are faithful messengers, but they are only messengers. The meaning they carry comes from elsewhere. It comes from people, from their ideas and their efforts and their care. And that means that when you use a device, when you open an app, when you listen to a voice in the dark, You are, in a small but real way, in contact with the people who made it. Not directly, not in a way they'll ever know about. But the connection is there, a thread of intention running from their mind to yours, through layers of code and hardware and network protocols, all of it designed to carry meaning faithfully from one person to another. The machines don't understand this connection. They don't need to. They just need to follow their instructions, fetch and execute, over and over, while the meaning flows through them like water through a pipe. The pipe doesn't know it's carrying water, it's just a pipe. But without the pipe, the water wouldn't reach its destination. The machines are the pipes. We are the water. We are the meaning. We always have been. So let the machines keep doing what they do. Let them keep counting, keep checking, keep routing packets and cycling through loops. They're good at it. They were built for it. And while they work, let yourself rest in the knowledge that you are connected, even now, even in the dark, to a vast network of human effort and human care. The person who wrote the program that plays this voice. The person who designed the compression algorithm that makes the audio small enough to stream. The person who laid the fiber optic cable that carries the data to your device. The person who assembled the phone on your nightstand. None of them know you personally. But they built something for you anyway. They built something for the person who would use it, whoever that turned out to be. And you, right now, are that person. You are the one the programs were written for. The alarm was set for you. The traffic light will change for you, or for someone like you, someone trying to get home safely. The voice is speaking to you, not to a generic audience, but to you, the specific person lying in this specific room, in this specific moment, listening. That's the quiet truth at the heart of all of this. The machines don't care about you. They can't. But the people who built the machines, who wrote the software, who designed the protocols, they did care. They built all of this so that it would work for someone. And tonight, that someone is you. Let that thought settle. Let it be a small warmth in the dark. You are not alone. You are surrounded by the results of human effort, human ingenuity, human care. The machines are just the delivery system. The gift itself comes from other people, from thousands of them, tens of thousands, across decades, across continents, each one adding their small contribution to the growing structure. Ada Lovelace, writing instructions for a machine that didn't exist. Grace Hopper, building the first compiler so that programmers could write in words instead of numbers. Vint Cerf and Robert Kahn, designing protocols so that machines could talk to each other across any distance. And all the others, the ones whose names you'll never know, who wrote the code for your phone's operating system, who tested the firmware for your router, who debugged the software that generates synthetic speech. All of them, in their own way, built something for you. The machines will keep working through the night. They don't need your gratitude. They don't need anything. But perhaps, as you drift towards sleep, you can feel a quiet sense of appreciation, not for the machines themselves, but for the human hands and minds that shaped them. For the fact that you live in a world where so many people, most of whom you'll never meet, have built things to make your life a little easier, a little safer, a little more connected. The alarm will wake you in the morning. The traffic light will help you get where you're going. The voice will fade into silence when the recording ends, having done what it was meant to do. And somewhere, a program is still counting, patiently, towards some number it will never mind reaching. It doesn't know why it's counting. It doesn't need to know. The counting was someone's idea, someone's intention, set in motion long ago, and now it continues, on its own, while the person who started it sleeps, or works, or has long since moved on to other projects. The program doesn't remember its creator, but the creator's intention is still there, embedded in the code, carried forward in time by a machine that never forgets, never tires, never stops until it's told to stop. You don't have to count with it. You don't have to match its pace or its persistence. You are not a machine. You are the reason the machine exists. You are the point. Without you, without the person on the other end, all of this would be meaningless. The programs would still run. The processors would still fetch and execute. The packets would still travel across the network. But there would be no one to benefit from it, no one to read the message or hear the voice, or wake up to the alarm. The machines need us to complete them. Without us, they're just patterns of electricity, running in empty loops, serving no purpose. With us, they become something more. They become carriers of meaning, of connection, of care. So rest now, in the knowledge that you matter to all of this. Not because you built it, but because you're the reason it was built. The machines are working for you tonight. Let them. They don't mind. They don't know what minding would even mean. They just do what they were told, faithfully, tirelessly, while you close your eyes and let the day fall away. The room is quiet, the lights are blinking, on and off, in patterns designed long before tonight. Everything is working as it should, and you, the person all of this was built for, can finally let go.